In the vast expanse of the universe, there exists a giant, a galaxy so massive and ancient that it has silently observed the birth of stars, the formation of planets, and the mysteries of time unfolding. This galaxy, Andromeda, is not just a collection of stars and dust, it's a cosmic puzzle, filled with secrets waiting to be uncovered. Despite being one of the closest galaxies to us, Andromeda still holds many of its deepest mysteries tightly within its spiral arms. But what if the story of Andromeda isn't just about the stars it holds, but the forces shaping it from the shadows? What if we are only beginning to understand its true role in the grand scheme of the universe? Join me as we journey through the enigma of Andromeda, where every twist and turn in this celestial giant might just lead to a discovery that will change everything we thought we knew about the cosmos. Floating quietly in the ink-black void, the Andromeda Galaxy is a titan in our cosmic neighborhood, a swirling island of more than 1 trillion stars, each a burning sun, encircled by clouds of gas, veils of dark matter, and ancient secrets older than the Earth itself. It is a place where entire solar systems are born and die, where black holes feast and galaxies collide, where time seems to stretch and warp beyond human understanding. And though it is over 2.5 million light-years away, meaning the light we see from it tonight left when early humans were first mastering fire, Andromeda's gravitational pull is already influencing us. We are, inevitably, on a collision course. But before we get lost in the sheer inevitability of this cosmic event, let's unravel the story of Andromeda. Because it is not just a galaxy. It is a portal into the deepest mysteries of the cosmos. Its origins, its future, and its colossal structure all pose questions that dig deep into the heart of everything we think we know about space, time, and existence itself. Andromeda, or M31, as astronomers formally call it, is the largest galaxy in our local group, a small congregation of about 54 galaxies dominated by Andromeda, our Milky Way, and the smaller Triangulum Galaxy, M33. At first glance, Andromeda may appear to be just another spiral galaxy, not unlike our own. But a closer inspection reveals how deceptive simplicity can be. Andromeda is immense. Stretching approximately 220,000 light-years across, it dwarfs the Milky Way in scale. Imagine traveling at the speed of light, 299,792 kilometers per second, and still taking more than 220,000 years just to cross from one edge of Andromeda to the other. Even at such impossible speeds, the sheer size boggles the mind. But its vastness is not simply an expanse of empty space. It is filled with matter, life-birthing gas clouds, stellar nurseries, and the remnants of ancient, long-dead stars whose cataclysms seeded the galaxy with the elements necessary for life as we know it. The galaxy's spiral arms, intricate and well-defined, are home to an unfathomable number of stars, some older than the solar system itself, others freshly ignited from the collapse of cold, dense gas clouds. These spirals are not static. They are dynamic, moving like the arms of a great galactic clock, each star orbiting a common center where, hidden in the heart of Andromeda, lurks a supermassive black hole millions of times the mass of our Sun. Scientists estimate the mass of Andromeda to be somewhere between 800 billion and 1.5 trillion solar masses. But what's even more fascinating is that most of this mass is invisible, composed not of stars, planets, or gas, but of dark matter, a mysterious and unseen substance that neither emits nor absorbs light. Dark matter is thought to form a vast halo around Andromeda, influencing the motion of its stars and satellite galaxies through gravity alone. It is one of the greatest unsolved mysteries of modern astrophysics. What is dark matter, and why does it seem to dominate the structure of the universe? Peering deep into Andromeda reveals another astonishing fact. This galaxy is not alone. Surrounding it are more than a dozen dwarf galaxies, many of which are being slowly devoured by Andromeda's insatiable gravity. Galaxies like M32 and M110 orbit Andromeda like moths circling a flame, their fates sealed by the colossal forces at play. Evidence suggests that Andromeda itself grew by cannibalizing smaller galaxies over billions of years, incorporating their stars into its sprawling arms and luminous core. If galaxies are cities of the cosmos, then Andromeda is an empire built upon conquest. The Andromeda Galaxy has been observed since ancient times. The Persian astronomer Abd al-Rahman al-Sufi described it in the 10th century as a small cloud, in his Book of Fixed Stars. To the naked eye, it appears as a faint, misty smudge in the night sky, best seen on dark, clear nights away from city lights. With the invention of the telescope, astronomers such as Simon Marius and later Edwin Hubble would transform our understanding of this enigmatic cloud. It was Hubble, famously, who proved in the 1920s that Andromeda was not merely a nebula within the Milky Way, as once believed, but an entirely separate galaxy millions of light-years away, thus shattering the prevailing notion of a universe limited to the confines of our own galaxy and expanding our cosmic horizons immeasurably. Andromeda's light carries stories across eons. Each photon striking our retinas tonight began its journey more than 2 million years ago, traveling across the abyss of intergalactic space, slipping past wandering black holes and clusters of galaxies to arrive here, offering a glimpse not of what Andromeda is now, but what it was when early Homo habilis first began to shape stone tools on a primeval Earth. In a very real sense, to look at Andromeda is to look back in time. Yet, for all its distance, Andromeda is not stationary. It is barreling toward us at a velocity of roughly 110 kilometers per second, faster than a bullet, faster even than most meteors entering Earth's atmosphere. In about 4.5 billion years, Andromeda and the Milky Way will collide in a titanic merger that will utterly reshape both galaxies. Stars will not collide directly, the distances between them are too vast, but the gravitational chaos unleashed will send entire solar systems, including possibly ours, careening into new orbits, or flinging them into deep intergalactic space. Over the course of billions of years, the two galaxies will intertwine, distort, and ultimately merge into a single, massive elliptical galaxy that some astronomers have already nicknamed Milkomeda. It will mark a new chapter in the cosmic story, one that will unfold long after humanity, as we know it, may have disappeared. But this looming collision isn't a cause for fear. Rather, it's a testament to the dynamic, ever-evolving nature of the universe. Galaxies are not static islands, but living, changing entities, constantly interacting, colliding, merging, and giving birth to new generations of stars. The Andromeda Galaxy, in many ways, is a microcosm of the universe itself, vast, mysterious, beautiful, and in constant motion. Its study offers insights not just into the fate of our own galaxy, but into the processes that have shaped the cosmos from the Big Bang to today, and beyond. Andromeda's beauty is only matched by its complexity. The galaxy's disk is tilted at about 77 degrees to our line of sight, giving it an elongated appearance through telescopes. Dust lanes, dark ribbons of cold interstellar matter, weave intricate patterns through its luminous arms, where stars are being born at a furious rate in glowing nurseries of gas and dust. At the core of Andromeda lies its beating heart, a supermassive black hole with a mass estimated at about 100 million times that of our Sun. Surrounding this black hole is a dense cluster of older stars, forming a bright, compact nucleus. Observations reveal that Andromeda's nucleus actually has two brightness peaks, a curious feature suggesting a complex history of mergers and interactions with other galaxies. Some theories propose that this double nucleus results from the infall of a smaller galaxy, whose core now orbits Andromeda's own. As we continue to study Andromeda with increasingly sophisticated instruments, from ground-based observatories to space telescopes like Hubble and the upcoming James Webb Space Telescope, we uncover more layers of its intricate story. We detect the faint echoes of past collisions, trace the streams of stars torn from long-digested galaxies, map the intricate motions of its satellites, and attempt to decipher the secrets locked in its oldest stars, secrets that date back to the infancy of the universe. As you peer into the Andromeda Galaxy, you are not just looking across space, you are staring deep into time itself. The light that reaches our eyes today began its journey 2.5 million years ago, long before the rise of modern humans, before our ancestors even mastered fire. That faint shimmer from the edge of existence has traveled unthinkable distances, passing through the silent cold of intergalactic space, untouched and unchanged, carrying secrets older than humanity itself. Andromeda, also known by its official astronomical designation M31, stands as the nearest spiral galaxy to our Milky Way. But calling it near is a relative term. It lies approximately 2.537 million light-years away, a gulf so vast that the mind can barely grasp it. Yet by cosmic standards, this is practically next door. If the universe were a sprawling city, Andromeda would be the neighboring metropolis just beyond a hazy river, visible from our windows on a particularly clear night. Its sheer scale dwarfs our own galaxy. Stretching over 220,000 light-years across, Andromeda is more than twice the size of the Milky Way. Where we have perhaps 200 to 400 billion stars, Andromeda is believed to boast 1 trillion. Imagine that, 1 trillion individual suns, each potentially surrounded by worlds of their own, endless possibilities orbiting in an intricate, gravitational ballet. Every speck of light within its spiraled arms could represent an entire solar system, countless realms of unknown wonders. Andromeda's mass is equally staggering. Early measurements once suggested it was significantly larger than the Milky Way in every sense, but more recent studies hint that the two galaxies might be roughly comparable in mass when including dark matter. Dark matter, that elusive, invisible material that neither emits nor absorbs light but reveals its presence through gravitational effects, constitutes a large portion of both galaxies' mass. Without dark matter, the beautiful structure of Andromeda's sprawling arms would collapse under its own gravity, as would our own galaxy. The beauty of Andromeda belies the forces at work within it. Spiral galaxies like Andromeda are not static, peaceful islands. They are dynamic, ever-changing systems, their stars and gas clouds in constant motion. Within Andromeda's glowing disk, newborn stars blaze into existence in regions of dense molecular clouds, while ancient stars die in spectacular supernova explosions. Black holes, some with masses millions of times that of our Sun, lurk at the centers of stellar clusters, warping space and time around them. At the very heart of Andromeda lies a monstrous supermassive black hole, far larger than the one anchoring the Milky Way. It feeds on stars and gas that wander too close, growing ever more massive over billions of years. Surrounding this gravitational juggernaut, stars race at breakneck speeds, caught in its overwhelming grip. It is a realm of violence and beauty, a cosmic forge where matter and energy dance the perilous waltz of gravity. But even Andromeda, colossal as it is, did not always exist in its current form. Its history, like ours, is written in collisions. Galaxies are not solitary wanderers. They are social creatures, drawn together by the invisible threads of gravity. Over billions of years, Andromeda has grown by devouring smaller galaxies, consuming them in epic mergers that reshaped its structure and fueled the birth of new stars. These ancient collisions left scars, streams of stars and gas, ghostly remnants of past conquests, still detectable by astronomers today. One of the most astonishing facts about Andromeda is its fate. It is on a collision course with us. Hurtling toward the Milky Way at speeds exceeding 110 kilometers per second, Andromeda and our galaxy are destined to meet in about 4.5 billion years. When that happens, the two galactic giants will not merely brush against each other, they will interpenetrate, stars flinging past one another, gravitational forces warping their spiral arms into wild new shapes. Despite the mind-boggling numbers of stars involved, direct collisions between individual stars will be rare, simply because space is so vast. Instead, the gravitational chaos will sculpt the two galaxies into a brand new entity, often referred to by astronomers as Milkomeda, or Milkdromeda, a giant elliptical galaxy, glowing with the blended light of two once separate stellar cities. This future collision is not a catastrophe to fear, but a majestic, slow-motion cosmic dance. Our night skies will transform over millions of years, growing ever brighter as Andromeda looms larger and larger, until it dominates the heavens in a breathtaking display. The Earth itself, unless disrupted by the Sun's evolution into a red giant, will witness this spectacle, a titanic galactic merger, played out across the entire dome of the sky. Studying Andromeda has taught astronomers profound truths about the universe. Its similarity to the Milky Way provides a template for understanding how spiral galaxies evolve, how stars are born and die, and how cosmic structures emerge over billions of years. Observations of Andromeda have unveiled the presence of dark matter, illuminated the life cycles of galaxies, and even hinted at the ultimate fate of our own cosmic home. Andromeda's satellites, smaller galaxies bound in orbit around it, also reveal a great deal about its gravitational influence and its violent history. Among these are the galaxies Messier 32 and Messier 110, both dwarfs that have been heavily distorted by Andromeda's gravitational pull. Trails of stars, ripped from these companions, weave intricate patterns around the galaxy, marking the echoes of ancient interactions. Even more intriguing is the discovery that Andromeda's satellite galaxies are not randomly scattered, as once thought, but instead seem to align along a vast, thin plane, a structure so unexpected that it challenges existing theories of galaxy formation. Why should they organize themselves in such a coherent, orderly fashion? No one fully knows. It suggests that our understanding of cosmic evolution may be missing critical pieces, hidden somewhere in the swirling mists of intergalactic space. Moreover, the stars within Andromeda tell stories spanning ages. Some are young and vibrant, burning hot and blue, while others are ancient, cool, and red, remnants of a universe much younger than today's. By studying the metallicity, the abundance of elements heavier than hydrogen and helium, of these stars, astronomers can trace the galaxy's history of star formation and galactic mergers, piecing together a vast, intricate puzzle spanning billions of years. The dust lanes threading through Andromeda's spiral arms mark regions of intense star formation. These dusty rivers are the nurseries where future stars, and perhaps planets, are being born even now. Within these clouds, gravity battles against internal pressure and magnetic fields, coaxing dense pockets of gas into collapse. When they finally give way, new suns ignite, their radiation carving luminous bubbles into the surrounding material, announcing their birth to the galaxy. Farther out, Andromeda's extended halo, a vast, diffuse cloud of stars, globular clusters, and dark matter, stretches tens of thousands of light-years beyond the main disk. This halo is a fossil record of Andromeda's violent past, a scattering of relics from ancient collisions, mergers, and accretions. Some of the oldest globular clusters in the universe orbit within this halo, their tightly packed stars bound together since shortly after the dawn of time. The Andromeda Galaxy is not just a marvel to behold, it is a cosmic laboratory, a place where astronomers can test theories of gravity, dark matter, star formation, and the ultimate fate of galaxies. Every observation, every spectrum, every photograph peels back another layer of mystery, revealing both answers and new questions. And yet, despite all we have learned, Andromeda remains full of enigmas. What is the true nature of the dark matter halo that binds it together? What unknown forces sculpted the strange alignment of its satellite galaxies? How will its final merger with the Milky Way truly unfold, and what new structures will emerge from that colossal collision? These are not questions of idle curiosity. They are questions that touch the deepest workings of the universe itself. Our connection to Andromeda is intimate and inescapable. One day, far in the future, long after humanity has evolved beyond its current form, or perhaps vanished entirely, the night sky will no longer feature the lonely arc of the Milky Way. Instead, it will blaze with the tangled remnants of two ancient galaxies, intertwined forever. Somewhere within that new creation, worlds will circle stars as they always have, perhaps harboring life that gazes upward and wonders at the same questions that stir our imagination today. Even now, as you listen, Andromeda moves closer, step by inevitable step. Its journey across the void is slow on human timescales but relentless on cosmic ones, a silent odyssey that began long before we were born and will continue long after we are gone. The universe is a place of endless wonder and ceaseless change, and Andromeda is one of its grandest reminders, a colossal testament to the beauty, the violence, the mystery, and the eternity of the cosmos. Where we marvel at the Milky Way's hundreds of billions of stars, Andromeda boasts upwards of 1 trillion, a staggering, almost incomprehensible number of suns, each potentially orbited by planets, moons, and entire systems beyond anything we can presently imagine. If we could somehow travel there and observe it from within, its night sky would blaze with countless brilliant stars, vastly outshining anything we see on Earth. It would be a realm of light and wonder, a realm where the darkness of space is forever softened by the omnipresent glow of nearby suns. But Andromeda is not merely an oversized sibling to the Milky Way. It is a galaxy rich with mysteries, scars of ancient cosmic battles, and untold stories written across its sprawling arms. Its vast spiral structure, so familiar yet so unique, is a frozen storm of motion, clusters of stars orbiting a supermassive black hole at its core, immense clouds of hydrogen gas forming new stars and vibrant nurseries, and aged red giants coasting silently through the galactic halo. One of the most profound realities about Andromeda is its destiny. It is on a collision course with the Milky Way. Astronomers have calculated, with chilling certainty, that in roughly 4.5 billion years, our two galaxies will meet in a cosmic embrace, a merger of staggering proportions. This event, often called Milkomeda or the Milky Andromeda, will not be a violent crash in the sense we experience on Earth. Instead, it will be a slow, majestic intertwining of two stellar giants, their shapes distorting, stars slingshotting into new orbits, and vast new regions of star formation lighting up the darkness. The night sky would change dramatically for any observers still living on Earth at that time. Long before the collision, Andromeda would swell in the sky, growing larger and more luminous until it dominates the heavens. Twin cores would eventually orbit each other, spiraling closer in a gravitational ballet, before finally merging into a single, enormous elliptical galaxy. In a universe that constantly expands and isolates galaxies from one another, this future union is both inevitable and profoundly rare. Yet Andromeda's story is not just about its future collision. It holds ancient secrets as well, evidence of past galactic cannibalism. Through painstaking observations, astronomers have detected long, faint streams of stars that arc around Andromeda, like spectral rivers. These are the remnants of smaller galaxies that ventured too close and were torn apart by Andromeda's immense gravitational pull, absorbed into its sprawling mass. Andromeda is, in many ways, a survivor and a predator, shaped by countless encounters and mergers over billions of years. When it comes to mass, Andromeda was once thought to significantly outweigh the Milky Way. Early measurements suggested it had far more mass, largely due to its greater number of visible stars and its apparent size. However, more recent studies that account for the elusive substance known as dark matter suggest that the Milky Way might be nearly as massive as Andromeda, or perhaps even slightly more. Dark matter, an invisible material that interacts only through gravity, makes up the majority of mass in both galaxies, cloaking them in enormous, unseen halos that stretch far beyond the visible stars. The Andromeda Galaxy is also home to an astonishing number of globular clusters, dense, spherical collections of ancient stars that orbit the galactic center. While the Milky Way has about 150 known globular clusters, Andromeda hosts more than 400. These ancient stellar relics, some nearly as old as the universe itself, serve as cosmic time capsules, preserving clues about the early conditions of galaxy formation. Another intriguing feature of Andromeda is its satellite galaxies. Much like the Milky Way is accompanied by the large and small Magellanic Clouds, Andromeda is orbited by dozens of smaller galaxies. Some of the more famous ones include Messier 32, M32, and Messier 110, M110, both of which are dwarf elliptical galaxies that dance in close proximity to Andromeda's majestic arms. These companions are locked in a gravitational relationship that has shaped Andromeda's evolution, and some may one day be absorbed entirely. Delving deeper into Andromeda's core reveals an even stranger truth. Nestled at its center lies a supermassive black hole, comparable to Sagittarius A** at the center of our own Milky Way. This behemoth has a mass equivalent to about 100 million times that of our Sun. It exerts a profound influence on the stars and gas near the galactic center, causing them to orbit at mind-bending speeds. Observations of Andromeda's nucleus have revealed a double structure, a lopsided brightness suggesting that the black hole may have captured a second, smaller black hole during a past merger, a haunting reminder of Andromeda's violent history. Andromeda's discovery is a tale that mirrors humanity's journey toward cosmic understanding. The earliest recorded observations date back more than 1,000 years to Persian astronomer Abd al-Rahman al-Sufi, who described it as a small cloud in his book of fixed stars around 964 AD. Yet it wasn't until the 20th century that its true nature was revealed. In the 1920s, American astronomer Edwin Hubble, after whom the Hubble Space Telescope is named, made the groundbreaking discovery that Andromeda was not a nebula within our galaxy but an entirely separate galaxy unto itself. Using observations of Cepheid variable stars, he measured its distance and forever changed our understanding of the universe, expanding it from a single galaxy to a vast cosmos filled with countless island universes. The technological feats that allow us to study Andromeda today are nothing short of miraculous. Telescopes like the Hubble Space Telescope, the Chandra X-ray Observatory, and the upcoming James Webb Space Telescope have captured its beauty in extraordinary detail, revealing star-forming regions, supernova remnants, and the cold dust that winds through its spiral arms. Radio telescopes have mapped the hydrogen gas that forms the raw material for new stars, showing how Andromeda continues to evolve even now. Intriguingly, Andromeda is not a static entity drifting through the void. It is moving toward us at approximately 110 kilometers per second, about 68 miles per second. This velocity is both a harbinger of our future collision and a clue about the gravitational forces at play on a cosmic scale. The local group, a collection of more than 50 galaxies including the Milky Way, Andromeda, and the Triangulum Galaxy, is bound together by gravity, resisting the general expansion of the universe on these relatively small scales. As we peer further into the future, scientists theorize that the eventual merger of Andromeda and the Milky Way will create a new, larger galaxy, possibly an elliptical one resembling the massive galaxies we see in the centers of other clusters. The stars themselves, despite the dramatic nature of the collision, are unlikely to physically collide due to the vast spaces between them. Instead, gravitational interactions will scramble their orbits, throwing many stars into long arcs and perhaps even ejecting some from the new galaxy entirely. Our solar system may not remain in its current orbit during this grand cosmic event. Some simulations suggest that it could be flung into a completely different part of the new galaxy, while others hint it might remain relatively undisturbed. Regardless, the night skies of any future Earth-like worlds would be transformed into breathtaking tapestries of stars, nebulae, and new stellar nurseries created by the gas compressed during the merger. Despite its proximity and grandeur, there is still so much about Andromeda that remains mysterious. What triggered its past mergers? How many civilizations, if any, have risen and fallen among its trillion stars? Could life exist on planets orbiting its suns, evolving under alien skies entirely separate from our own cosmic story? These questions haunt astronomers and dreamers alike, driving us to look deeper, to send our minds soaring across the intergalactic gulf. Andromeda's sheer presence challenges us to think on timescales and distances far beyond our everyday experience. It reminds us that our place in the cosmos is both infinitesimally small and yet intimately connected to a grand, unfolding narrative of creation, destruction, and rebirth. The very atoms in our bodies, forged in the hearts of ancient stars, echo the same processes happening right now in Andromeda's distant arms. And so, when we look up at the Andromeda Galaxy on a clear, dark night, we are not just seeing a distant smudge of light. We are witnessing a reflection of ourselves, a whisper from the distant past, and a glimpse into a future we cannot escape. It is a silent sentinel, watching across the darkness, inviting us to imagine, to wonder, and to reach beyond the boundaries of our small world into the endless frontier beyond. At the heart of Andromeda lies another secret, a supermassive black hole, millions of times the mass of our Sun. This monstrous entity anchors the galaxy, commanding the motion of countless stars within its gravitational influence. Surrounding it is a bustling hub of activity, a dense core where ancient stars whirl in intricate orbits, and where traces of past galactic mergers are preserved like cosmic fossils. In fact, evidence suggests that Andromeda has already consumed multiple smaller galaxies during its long history, growing larger and more complex with every collision. The galaxy itself is not static. Observations have revealed that Andromeda is ringed by enormous streams and shells of stars, remnants of past galactic meals, torn apart and stretched across space by tidal forces. These star streams are the telltale scars of cosmic cannibalism, and they hint at a violent past far bloodier than Andromeda's serene appearance would suggest. Every ripple in its structure, every asymmetry in its arms, every faint halo of dispersed stars tells a story of ancient cosmic violence and survival. Andromeda's majestic spiral arms are themselves sites of furious creativity and decay. Vast regions within the arms, dense with molecular gas, act as star-forming nurseries where new suns are born in blazing brilliance. However, not all regions teem with such youthful energy. In many areas, especially toward the galaxy's edges, the birth of new stars has slowed dramatically, leaving fields of aging stars to drift quietly, slowly burning out their fuel in lonely twilight. One of the most stunning features of Andromeda, visible through powerful telescopes, is its dual nucleus. When astronomers first peered deeply into the galactic center, they discovered not one but two bright cores. This peculiar feature was initially baffling, leading to intense debate and speculation. It is now believed that the double nucleus is the result of a densely packed star cluster orbiting the central black hole, a gravitational oddity that gives the illusion of two centers instead of one. Beyond the visible splendor of Andromeda lies a darker, more elusive component, its dark matter halo. Though invisible to the eye, dark matter makes up the vast majority of Andromeda's mass, enveloping the galaxy in an immense, unseen cloud. Its presence is inferred by the way it affects the motion of stars and gas, binding the galaxy together and influencing its future merger with the Milky Way. Dark matter is the ghostly scaffolding of the universe, and Andromeda is no exception. It swims through this shadowy ocean, shaped and cradled by forces we have yet to fully understand. In addition to its main structure, Andromeda is accompanied by an entourage of at least 35 known satellite galaxies, including the well-known M32 and M110. These smaller companions orbit the giant like moths around a flame, many of them slowly being drawn closer, destined either to be torn apart by tidal forces or to plunge into Andromeda itself. Some of these satellites are rich in gas and active in star formation, while others are little more than ghostly relics, their stellar populations ancient and depleted. Andromeda's satellites offer critical clues to the broader architecture of our local cosmic neighborhood, known as the local group. This loose collection of over 50 galaxies, dominated by Andromeda and the Milky Way, forms a gravitationally bound system that drifts through the vastness of the universe, itself only a tiny portion of an even larger structure, the Virgo supercluster. Understanding the dynamics of Andromeda and its satellites is key to deciphering the ultimate fate of the local group, a fate inexorably tied to the impending galactic merger. Even more fascinating is the realization that the collision between Andromeda and the Milky Way is not a rare event in the cosmic narrative. Galactic mergers are fundamental processes in the evolution of the universe, playing critical roles in the growth and transformation of galaxies. Every star you see, every planet, every atom within those systems has, at some point, been shaped by ancient collisions and mergers. In studying Andromeda, we glimpse not only our own future but also the fundamental mechanics of cosmic evolution on the grandest scales. The discovery and study of Andromeda is a story woven through centuries of human curiosity. Although ancient astronomers like the Persian polymath Abd al-Rahman al-Sufi catalogued it in the 10th century as the little cloud, it wasn't until the 20th century that its true nature was understood. Edwin Hubble, through meticulous observation of Cepheid variable stars within Andromeda, determined its vast distance from Earth. This discovery was revolutionary. It proved that the universe was far larger than previously imagined and that the Milky Way was but one galaxy among countless others. Hubble's revelation exploded the scale of the cosmos overnight, catapulting humanity's understanding of our place in the universe into an entirely new realm. What was once a faint, enigmatic blur in the sky became a grand, independent galaxy, a majestic rival to our own, and a mirror through which we could glimpse the profound complexity of existence itself. Today, Andromeda continues to captivate both professional astronomers and casual stargazers. It remains one of the few galaxies visible to the naked eye from Earth under dark skies, offering a direct, tangible link to the universe beyond our solar system. For many, a glimpse of Andromeda is a humbling experience, a fleeting, silent connection to the vast theater of creation and destruction unfolding over unimaginable timescales. Our technological advancements have allowed us to peer deeper into Andromeda than ever before. Telescopes like the Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories armed with cutting-edge instrumentation have peeled back layer after layer of mystery, revealing an intricate web of stars, gas, and dark matter stretching far beyond what our ancestors could have dreamt. Yet with every answer comes new questions, deeper enigmas that hint at realms of knowledge still tantalizingly out of reach. If Andromeda teaches us anything, it is that the universe is a place of relentless change, of awe-inspiring beauty born from chaos and destruction. It is a reminder that even the mightiest structures in the cosmos are transient, evolving across billions of years, reshaped by forces beyond comprehension. The galaxy's serene appearance belies a history of violence and transformation, a cosmic odyssey written across a canvas of unimaginable scale. In contemplating Andromeda, we are also contemplating ourselves, our origins, our future, and our fragile, fleeting place within the grandeur of the universe. We are stardust, born from the ashes of ancient suns, gazing outward into the depths from whence we came, and forward into a future where our descendants, if they endure, will witness the birth of a new galaxy forged from the bones of the Milky Way and Andromeda. Beyond its bright, starry core and majestic arms, Andromeda possesses an enormous halo of dark matter, a mysterious, invisible substance that makes up the vast majority of the galaxy's total mass. Though dark matter cannot be seen directly, its presence is betrayed by the way it bends the paths of stars and gas clouds, exerting gravitational influence far beyond what visible matter alone could achieve. Without this dark halo, Andromeda's stars would not orbit as they do, the galaxy would not hold together. In fact, without dark matter, Andromeda, the Milky Way, and virtually every galaxy in the universe would fly apart, unable to sustain their magnificent structures. Astronomers estimate that up to 90% of Andromeda's mass is composed of dark matter. Yet despite decades of research, the true nature of dark matter remains one of the greatest unsolved mysteries of modern science. It is an invisible scaffolding, a hidden framework that shapes the cosmos on the largest scales, and Andromeda stands as a majestic monument built upon this unseen foundation. Surrounding Andromeda is a retinue of smaller companion galaxies. Over a dozen dwarf galaxies orbit around it like a royal court circling a sovereign. Some of these companions, such as M32 and M110, are close enough to be seen through amateur telescopes. These dwarfs are not just passive followers. They interact gravitationally with Andromeda, occasionally passing through its disk, triggering waves of star formation, or becoming stretched and distorted by its massive gravitational pull. In time, many of these dwarf galaxies may be completely consumed by Andromeda, adding their stars and gas to the larger galaxy's sprawling expanse. The structure of Andromeda itself is more complex than it first appears. While it is commonly depicted as a classic spiral galaxy, detailed observations have revealed that Andromeda is slightly warped. Its disk is not perfectly flat. Rather, it is twisted and bent, likely due to gravitational interactions with its companion galaxies or past mergers. Moreover, its spiral arms are not rigid structures but are constantly evolving, shaped by the movement of stars, gas dynamics, and invisible dark matter substructures weaving through the galactic plane. Even the colors of Andromeda tell a story. Its bright core shines with a yellowish hue, populated by older, redder stars that have exhausted much of their hydrogen fuel. In contrast, its spiral arms glow bluish in regions where young, hot stars burn fiercely, marking the sites of active star formation. This distribution of stellar populations paints a vivid portrait of a galaxy both ancient and youthful, a cosmic entity forever caught between the memories of its primordial past and the promise of its unfolding future. When astronomers peer deep into Andromeda using powerful telescopes, they not only observe its present state but also glimpse snapshots of its history. Embedded within its structure are globular clusters, ancient, spherical groups of stars tightly bound together, some of which may be among the oldest surviving relics from the early universe. These clusters act like cosmic time capsules, preserving information about the conditions that prevailed during the earliest epochs of galactic formation. By studying them, scientists hope to unlock the secrets of how galaxies like Andromeda, and indeed the Milky Way itself, came into being. The study of Andromeda also holds profound implications for the future of humanity. As the nearest spiral galaxy, it serves as a natural laboratory for understanding galaxy dynamics, star formation, and cosmic evolution. Every insight gleaned from Andromeda deepens our understanding of our own place in the universe, offering clues about how galaxies live, grow, collide, and eventually die. One of the most awe-inspiring aspects of Andromeda's story is how it ties into our own destiny. The approaching merger between Andromeda and the Milky Way is not merely a scientific curiosity. It is a reminder that even galaxies are impermanent. Though the event is billions of years away, it highlights the ever-changing nature of the cosmos. Our descendants, if they exist billions of years from now, will gaze at a night sky utterly transformed, where Andromeda no longer appears as a faint smudge, but as a looming titan filling much of the heavens, its stars mingling with ours in a celestial tapestry of staggering beauty. Even today, the motion toward collision is detectable. Precise measurements show that Andromeda is moving toward us at a speed of about 110 kilometers per second. This movement was first suspected in the early 20th century by astronomer Vestal Melvin Slipher, whose observations of the galaxy's blue-shifted light provided the first hints that it was approaching rather than receding. Later, Edwin Hubble's groundbreaking work clarified that Andromeda was not a mere nebula within our galaxy but a vast, separate galaxy in its own right, a realization that fundamentally altered humanity's understanding of the universe. The realization that there are countless galaxies beyond our own, and that Andromeda is but one of billions scattered across the cosmos, expanded the scale of the known universe by orders of magnitude. In a single stroke, humanity was forced to confront a cosmos far grander and more humbling than anyone had previously dared to imagine. And at the heart of that revelation stood Andromeda, a beacon from beyond, inviting us to explore, to question, and to dream. The discovery of Andromeda's true nature ignited a new era of astronomical exploration, leading to some of the most profound questions humanity has ever asked. Are there planets within Andromeda's countless star systems capable of supporting life? Could civilizations have arisen there, parallel to our own, separated by the vast gulf of intergalactic space? If so, could the merger of our galaxies one day bring distant civilizations closer together? Or would they remain forever isolated by the sheer immensity of the void? Though these questions remain unanswered, they speak to the deep human longing to understand our place in the cosmos, a longing that Andromeda continues to inspire. Every photon of light we capture from that distant galaxy is a message from the past, a whisper across millions of years, a testament to the endurance of beauty and mystery across unimaginable spans of time and space. Each of these dwarf galaxies tells a story of survival against overwhelming odds. Some show signs of tidal disruption, where Andromeda's immense gravitational pull stretches and warps their structures, stealing their stars in long, flowing streams that weave through space. Others remain surprisingly intact, resilient islands of light clinging to existence in the vast darkness. Together, they offer a glimpse into the complex and dynamic processes that govern galaxy formation and interaction across the universe. But Andromeda's story is not written solely in the present. Its past is inscribed in the movements of its stars, in the temperature of its gas clouds, and in the faint, ghostly structures that spiral around it. By studying the composition and behavior of these features, astronomers have pieced together a rough history of Andromeda's growth. It likely formed through a series of mergers, absorbing smaller galaxies over billions of years, each event leaving subtle fingerprints behind. Some of the faint arcs and ripples seen in its outer halo are the remnants of these ancient mergers, frozen waves in the cosmic sea that mark times of tremendous upheaval. In examining Andromeda's chemical composition, scientists have found that its stars are, on average, slightly older and more metal-rich than those in the Milky Way. Metals, in astronomical terms, refer to any elements heavier than helium, the building blocks of planets, life, and complexity. A higher metal content suggests that Andromeda's star-forming activity was vigorous in the past, churning out generations of stars that enriched the interstellar medium with heavier elements through processes like supernova explosions. Andromeda's disk, while still hosting areas of star formation, shows signs of slowing down. Compared to younger, more active galaxies, Andromeda seems to be gradually transitioning into a quieter phase of its life. Star formation rates are declining, the raw materials needed to birth new stars are being used up or dispersed, and its overall structure is settling into a more stable, mature form. Yet despite this slowdown, the galaxy remains a vibrant, dynamic system, and its future holds even greater transformations. When astronomers first measured Andromeda's motion relative to the Milky Way, they discovered it is moving toward us at an astonishing speed of about 110 kilometers per second. This inexorable journey is not merely a drift through the void. It is the inevitable result of mutual gravitational attraction between two colossal islands of stars. Although it will take billions of years for the actual collision to unfold, the path is already set, and the outcome, a cosmic merging of breathtaking scale, is assured. As the two galaxies draw closer, their immense gravitational fields will begin to distort each other. Long before the actual merger, tides of stars and gas will start to stretch between the two, forming vast bridges and streams across intergalactic space. Entire star systems may be flung into new orbits, and some may even be ejected entirely, becoming lonely wanderers of the intergalactic medium. During the height of the collision, Andromeda's elegant spiral arms will be torn apart, and its structure will warp into complex, chaotic forms. Eventually, after hundreds of millions of years of interaction, a new galaxy will emerge from the ruins, an enormous elliptical galaxy, far larger and more massive than either Andromeda or the Milky Way alone. This new galaxy will shine brightly in the local universe, a testament to the awesome power of gravitational forces acting over vast timescales. The night skies of any surviving civilizations within these merging galaxies will be transformed into a spectacle beyond imagination, filled with countless brilliant stars and sprawling, shifting clouds of gas illuminated by bursts of new star formation. The question arises, what will happen to our own solar system during this cosmic event? Current models suggest that while the odds of a direct collision with another star are extremely low, the gravitational upheaval could alter the Sun's orbit around the galactic center. Our solar system might find itself flung into a different part of the new galaxy or cast adrift into the far reaches of intergalactic space. Though humanity may not be around to witness it, the ultimate fate of the Earth and its companions will be intimately tied to the outcome of this grand cosmic merger. Peering further into Andromeda's structure, astronomers have also uncovered regions of intense radio emissions, X-ray sources, and even potential evidence of intermediate-mass black holes, smaller than the central supermassive black hole but still massive enough to influence the dynamics of their local environments. These hidden features reveal that Andromeda is far from a uniform or simple system. It is a galaxy layered with complexity, each component telling a different story about the forces that shaped it. Modern telescopes, both ground-based and spaceborne, have allowed us to map Andromeda in extraordinary detail. Observations from the Hubble Space Telescope, for example, have resolved individual stars within the galaxy, enabling scientists to study its stellar populations with unprecedented precision. Infrared observations have pierced through dust clouds to reveal hidden star-forming regions, while ultraviolet surveys have highlighted the hot, young stars blazing in its spiral arms. These observations have not only deepened our understanding of Andromeda itself but have also provided crucial insights into galaxy formation and evolution more broadly. By comparing Andromeda's structure and behavior with that of other galaxies at different stages of their life cycles, astronomers can build models of how galaxies grow, interact, and change over cosmic time. As we delve deeper into Andromeda's nature, it's worth considering the broader implications of our cosmic neighborhood. Andromeda, the Milky Way, and several smaller galaxies form the local group, a collection of over 50 galaxies bound together by gravity. The study of this small group offers astronomers a unique opportunity to observe how galaxies evolve in a relatively compact, well-defined area of the universe. The local group, though relatively small compared to the vastness of the universe, serves as a microcosm for the grander processes of cosmic evolution. Andromeda's role within this group is significant. It is the largest galaxy in the local group, and its impending collision with the Milky Way is often cited as one of the most intriguing events on the horizon for cosmologists. But it's not just the size of Andromeda that draws attention, it's its history, its complex interactions with neighboring galaxies, and the insight it offers into the dynamics of galaxy mergers. Understanding Andromeda's evolution could hold the key to understanding the fate of the Milky Way and the future of galaxies like ours. The role of dark matter in this galactic dance is also a subject of immense interest. While we can't directly observe dark matter, we know it exists because of its gravitational effects on visible matter. Andromeda, like the Milky Way, is thought to be surrounded by a massive halo of dark matter. This dark matter plays a crucial role in the galaxy's formation and evolution, acting as a sort of gravitational scaffold that shapes its structure. Despite its invisibility, dark matter is a powerful force in the universe, influencing the movement of stars, gas, and even dwarf galaxies in Andromeda's vicinity. The study of Andromeda's dark matter is ongoing, and new methods, such as gravitational lensing, are being employed to map out its distribution more accurately. This dark matter halo likely extends far beyond the visible edge of the galaxy, providing the extra mass needed to hold Andromeda together despite the gravitational forces at play from its smaller neighbors. Without this unseen mass, the galaxy would not be able to maintain its structure. As we learn more about the dark matter that surrounds Andromeda, we also learn more about the nature of dark matter itself, an enigma that has puzzled scientists for decades. One of the most intriguing aspects of Andromeda is its supermassive black hole at the center. This black hole, known as M31*, is located at the core of the galaxy and has a mass that is roughly 100 million times that of the Sun's supermassive black holes. Like M31*, are thought to be present in the centers of most large galaxies, and they play a key role in the evolution of these galaxies. The exact mechanisms by which these black holes form and grow are still not fully understood, but it is clear that they have a profound impact on their host galaxies. In the case of Andromeda, M31* is surrounded by a complex region of hot gas, and scientists believe that it may be slowly feeding on the surrounding material. The immense gravitational pull of the black hole can cause nearby gas to spiral inward, heating it to millions of degrees and emitting X-rays that can be detected by space telescopes. This process, known as accretion, is one of the most energetic phenomena in the universe. However, despite the immense energy produced by the accretion of matter, M31* has not shown the same level of active quasar-like behavior that is sometimes seen in other galaxies. Instead, the supermassive black hole in Andromeda is relatively quiet compared to those in galaxies like the Milky Way. This could be due to the fact that Andromeda's central black hole has already consumed much of the surrounding gas and is in a more stable phase of its life cycle. Alternatively, it could be the result of Andromeda's ongoing evolution, with the galaxy's slower rate of star formation and reduced gas supply limiting the fuel available to the black hole. While the exact future of M31* remains uncertain, it is clear that it will play a central role in the merger between Andromeda and the Milky Way. As the two galaxies draw closer and their structures begin to merge, the supermassive black holes at their centers may eventually collide and coalesce into an even larger black hole. This cataclysmic event would release an immense amount of energy, sending ripples through the fabric of space-time itself in the form of gravitational waves. But the consequences of the Andromeda-Milky Way merger go beyond the black holes at their cores. The interaction between the two galaxies will likely cause widespread disruption in their stellar populations. Stars will be flung into new orbits, some even ejected from the newly formed galaxy altogether. The gas and dust that fill the space between stars will also be disturbed, possibly triggering new waves of star formation. The result will be a galaxy that is dramatically different from either Andromeda or the Milky Way, a giant elliptical galaxy, with stars scattered across its vast center, and a quiet, smooth disk that contrasts sharply with the chaotic, lively spiral structures of the past. Despite the cataclysmic nature of these cosmic events, the future of life on Earth remains uncertain. While the chances of our solar system being directly affected by the merger are low, the effects on the galaxy as a whole could still have indirect consequences for life on our planet. The redistribution of stars and interstellar gas might alter the cosmic environment in ways that are difficult to predict, and the long-term gravitational effects could lead to shifts in the orbits of stars, planets, and even entire solar systems. For now, though, we can only wait and observe as Andromeda continues its long journey toward the Milky Way. With each new discovery, we come closer to understanding the forces that drive the formation and evolution of galaxies. And as we gaze up at the night sky, we are reminded that the universe is a dynamic, ever-changing place, where galaxies collide, stars are born, and the very fabric of space-time itself is constantly reshaped. As we continue to explore the story of Andromeda, we must also consider the role of its spiral arms. These beautiful structures are not merely aesthetic, they are dynamic, evolving features of the galaxy, shaped by both gravitational forces and the movement of gas and stars. The arms of Andromeda are composed of vast clouds of gas and dust, alongside regions of intense star formation. These star-forming regions, known as HI regions, are where the next generation of stars are born. They glow brightly in the ultraviolet light emitted by young, hot stars and are some of the most striking features of the galaxy when viewed in optical wavelengths. But the formation of these spiral arms is not as simple as it might seem. They are not static structures but rather features that evolve over time. The spiral arms of galaxies like Andromeda are thought to form through a combination of factors, including the gravitational influence of the galaxy's central bulge, the density waves traveling through the disk, and the complex interactions between stars and gas. These arms can be thought of as waves of density that propagate through the galaxy, compressing gas and triggering star formation in their wake. Interestingly, the arms of Andromeda are somewhat asymmetric. The galaxy's western arm is more tightly wound, while the eastern arm is more loosely structured. This asymmetry is believed to be the result of interactions with nearby galaxies, particularly the smaller galaxies that orbit Andromeda. These interactions can disturb the gravitational balance of the galaxy, causing its spiral structure to become distorted over time. One of the most intriguing aspects of Andromeda's spiral structure is its large central bulge. This bulge, a dense concentration of stars at the heart of the galaxy, houses a population of older stars. The bulge plays a key role in the galaxy's dynamics, affecting the motion of stars and gas in the galaxy's disk. It is thought that the bulge formed early in the galaxy's history, possibly as a result of the merging of smaller galaxies that were later absorbed into Andromeda. As a result, the stars in the bulge are older and more metal-rich than those in the outer regions of the galaxy. As we look deeper into the galaxy, we begin to notice the complex interplay between the stars, gas, and dark matter. Dark matter, as we've discussed, makes up a large portion of the galaxy's mass, though it remains invisible to direct observation. However, its presence can be inferred from the behavior of visible matter, such as the way stars move within the galaxy's disk. The gravitational effects of dark matter are what keep Andromeda from falling apart under its own gravity. Without dark matter, the galaxy would not have enough mass to hold itself together, and its stars would drift apart. In fact, much of Andromeda's overall structure is shaped by the influence of dark matter. The galaxy's halo, an extended region of dark matter that surrounds its visible components, extends far beyond the edge of the disk, providing the additional mass required to maintain its gravitational stability. As we continue to learn more about dark matter, Andromeda offers a valuable laboratory for studying this mysterious substance, as it provides a relatively close and accessible example of how dark matter affects the formation and behavior of galaxies. Andromeda's interactions with other galaxies in the local group are another critical aspect of its evolution. As we mentioned earlier, Andromeda is on a collision course with the Milky Way, but it is also involved in a complex gravitational dance with several smaller galaxies. These smaller galaxies, known as satellites, orbit Andromeda and contribute to its overall mass. Some of these satellites are being slowly pulled toward the galaxy, where they will eventually be consumed, adding their stars and gas to the growing mass of Andromeda. Others are being stripped of their material by the gravitational forces of the larger galaxy, with their stars and gas being swept into the galactic halo. Over the course of billions of years, this process of accretion will continue, with Andromeda growing ever larger as it absorbs its smaller neighbors. This process is thought to be common among galaxies, as larger galaxies tend to absorb smaller ones in their vicinity. In fact, many of the large galaxies we see today, including the Milky Way, likely grew to their current size through a series of mergers and accretions of smaller galaxies. But Andromeda's future is not only shaped by its interactions with other galaxies. The galaxy is also influenced by the cosmic environment in which it resides. Galaxies like Andromeda are not isolated entities. They exist within a larger cosmic web, a vast network of galaxies, clusters, and dark matter that stretches across the universe. The local group, the collection of galaxies to which Andromeda belongs, is part of a much larger supercluster of galaxies known as the Virgo supercluster. This supercluster, along with others like it, forms a vast structure that spans billions of light-years. The forces at play in this larger cosmic web can have a profound effect on the evolution of galaxies like Andromeda. The gravitational pull of nearby galaxies and clusters can distort the structure of Andromeda, altering its motion and causing it to interact with other galaxies in ways that are not yet fully understood. These cosmic interactions are a key part of the larger story of galaxy formation, and studying Andromeda's place in this web can provide valuable insights into how galaxies evolve over time. As we look to the future, the merging of Andromeda and the Milky Way will mark a significant milestone in the evolution of our cosmic neighborhood. But the story of Andromeda is far from over. Even after the two galaxies collide and merge, Andromeda will continue to evolve, adapting to the new environment created by the merger. The resulting galaxy, with its new structure and stellar population, will be a testament to the forces of gravity and time that shape the cosmos. In the distant future, the stars of both Andromeda and the Milky Way will be scattered across the sky in new and unexpected configurations. The constellations we know today will be long gone, replaced by entirely new patterns of stars. The Sun, too, will find itself in a new cosmic environment, orbiting within a completely different galaxy. But whether or not life will still exist on Earth remains a question for another time. What is certain, however, is that Andromeda will continue to serve as a beacon for astronomers and stargazers alike. It is a galaxy full of mystery, beauty, and complexity, a symbol of the dynamic and ever-changing nature of the universe. As we continue to study Andromeda, we uncover not only the secrets of this distant galaxy but also the fundamental processes that govern the formation and evolution of galaxies throughout the universe. In many ways, Andromeda is our cosmic mirror, a reflection of what the Milky Way will one day become. By studying Andromeda, we are learning about our own future and gaining insights into the nature of the universe itself. The story of Andromeda is far from finished, and as we continue to explore this fascinating galaxy, we will undoubtedly uncover even more surprises and mysteries that will continue to inspire awe and wonder for generations to come. As we move forward in our exploration of Andromeda, it's important to delve deeper into its interaction with the larger cosmic structures surrounding it. Andromeda is not a solitary galaxy, but rather a member of the local group, a small cluster of galaxies that also includes the Milky Way, the Triangulum Galaxy, and a handful of smaller satellite galaxies. These galaxies are gravitationally bound, meaning they orbit each other and are connected in a complex cosmic dance. The dynamics of the local group are fascinating in themselves, as the galaxies are constantly moving and influencing one another's paths through space. The Milky Way, which is Andromeda's closest and most massive neighbor, has been interacting with Andromeda for billions of years. However, it is not just the Milky Way that has an impact on Andromeda's future. Andromeda also influences its neighboring galaxies, including the smaller members of the local group. One of the most striking features of Andromeda is its gravitational reach, which is vast and extends beyond its immediate surroundings. The galaxy's immense mass affects the motion of its smaller satellite galaxies, such as the M32 and M110, which orbit it in elliptical orbits. Some of these satellite galaxies are being slowly drawn toward Andromeda, with their stars and gas being absorbed into the larger galaxy. These satellite galaxies are a valuable source of information about the process of galaxy accretion, as they provide a glimpse into the fate of smaller galaxies that are consumed by larger ones. By studying these satellite galaxies, astronomers can gain insight into how galaxies grow and evolve over time, and how interactions with other galaxies shape their structure and composition. One of the most intriguing aspects of the local group, and the Andromeda Galaxy's role within it, is the eventual collision between the Milky Way and Andromeda. This monumental event, which will occur in about 4 billion years, will fundamentally change the structure of both galaxies. As the two galaxies approach each other, they will begin to experience tidal forces, which will distort their shapes and trigger a variety of cosmic phenomena, such as the formation of new stars and the disruption of existing ones. As the collision progresses, the two galaxies will pass through one another, their stars mostly unaffected due to the vast distances between individual stars. However, the gas and dust within the galaxies will collide and interact, causing the formation of new stars in what will likely be an intense and chaotic process. Over time, the two galaxies will begin to merge, their gas clouds blending together to form a single, larger galaxy. This process will take place over billions of years, but the final result will be a new galaxy, possibly an elliptical galaxy or a more irregular shape, that will mark the end of the Milky Way and Andromeda as separate entities. The Milky Way-Andromeda collision is not the only major interaction occurring in the local group. The Triangulum Galaxy, another nearby spiral galaxy, is also a member of this cosmic family. Though it is much smaller than Andromeda and the Milky Way, the Triangulum Galaxy plays an important role in the dynamics of the local group. Triangulum is currently in a relatively stable orbit, but it is expected to eventually be affected by the gravitational influence of both Andromeda and the Milky Way. It may even be pulled into the merger between the two larger galaxies, contributing its stars and gas to the formation of the new galaxy that will emerge from the collision. Beyond the local group, Andromeda is also part of a larger structure known as the Virgo supercluster. The Virgo supercluster is one of the largest known collections of galaxies, and it contains thousands of galaxies, including the Milky Way and Andromeda. The supercluster itself is part of an even larger structure called the Laniakea supercluster, a vast network of galaxies that spans more than 500 million light-years. These massive structures are the largest known gravitationally bound systems in the universe, and they provide a context for understanding the movement and evolution of galaxies on the grandest scales. Within the Virgo supercluster, Andromeda occupies a relatively central position. This means that it is not just moving in isolation, rather, it is influenced by the gravitational pull of other galaxies within the supercluster. The motion of Andromeda, along with the other galaxies in the local group, is part of a larger-scale movement known as the motion of the local group toward the Virgo cluster. This motion, which is caused by the gravitational attraction of the massive galaxies in the Virgo cluster, will eventually bring the local group closer to the cluster. One of the most interesting aspects of the motion of galaxies within superclusters is the concept of the Great Attractor. The Great Attractor is a mysterious and massive concentration of galaxies located in the direction of the Centaurus and Hydra constellations. It is the source of a gravitational anomaly that is pulling galaxies, including those in the local group, toward it at incredible speeds. The exact nature of the Great Attractor remains a mystery, but it is believed to be a supermassive concentration of galaxies and dark matter that exerts a powerful gravitational pull on surrounding galaxies. As we step back and look at the larger scale of the universe, the future of Andromeda and the Milky Way becomes even more intriguing. These two galaxies, along with their smaller neighbors, are part of a much larger cosmic web of galaxies, clusters, and superclusters that stretch across vast distances. Over billions of years, these galaxies will continue to evolve, merge, and interact, shaping the structure of the universe as a whole. The future collision between Andromeda and the Milky Way is not just a local event within the local group. It is a part of a larger pattern of galactic evolution that has been taking place throughout the universe. The merging of galaxies is a common process in the life cycle of galaxies, and it plays a critical role in their growth and transformation. As galaxies collide and merge, they can trigger bursts of star formation, create new structures like elliptical galaxies, and even influence the formation of black holes. In fact, it is believed that the merger between Andromeda and the Milky Way could lead to the formation of a supermassive black hole at the center of the new galaxy. Both Andromeda and the Milky Way currently host supermassive black holes in their centers, and as the galaxies merge, these black holes will likely come together, eventually forming a single, even more massive black hole. This process will be an incredibly slow and violent one, taking billions of years to unfold, but it will be a key part of the new galaxy's evolution. As we continue to explore the mysteries of Andromeda, we are not just learning about a single galaxy. We are gaining insight into the fundamental processes that govern the behavior of galaxies throughout the universe. From the formation of stars and gas clouds to the collision and merging of entire galaxies, Andromeda offers us a unique opportunity to study the forces that shape the cosmos on the largest scales. By understanding Andromeda, we can learn not only about our own future but also about the past and future of the universe itself. The story of Andromeda is not just the story of one galaxy. It is the story of the cosmos, of how galaxies form, evolve, and interact over cosmic time. It is a tale of creation and destruction, of the forces that shape the universe and the stars that light up the night sky. And as we continue to study this magnificent galaxy, we will undoubtedly uncover even more secrets that will help us understand the nature of the universe and our place within it. As we look even deeper into the complexities of Andromeda, we begin to understand not just its structure, but its role in the wider universe. One fascinating aspect of Andromeda's cosmic journey is its interaction with dark matter. Dark matter, the mysterious and invisible substance that makes up a significant portion of the mass in the universe, plays a crucial role in shaping galaxies, including Andromeda. While we cannot directly observe dark matter, its gravitational effects are apparent in the motion of stars and gas within galaxies. Andromeda, like the Milky Way, is thought to contain a massive halo of dark matter, a spherical region extending far beyond the visible stars and gas in the galaxy. This dark matter halo is believed to be responsible for the galaxy's overall stability and structure. Without the gravitational influence of dark matter, galaxies like Andromeda would likely not be able to hold together. The invisible presence of dark matter affects the orbits of stars and the motion of gas clouds, giving the galaxy the gravitational pull needed to maintain its spiral shape and prevent it from flying apart. As scientists continue to study dark matter, they look to galaxies like Andromeda to understand how this mysterious substance behaves. One interesting observation is that the distribution of dark matter around Andromeda appears to be less concentrated in the center of the galaxy compared to other galaxies. This suggests that the dark matter halo of Andromeda may be more diffuse, possibly offering clues about its history and the forces that have shaped it. By studying Andromeda's dark matter, astronomers hope to gain a better understanding of how galaxies form and evolve, and how dark matter itself might interact with visible matter. Another intriguing aspect of Andromeda is its stellar population. As one of the largest and most massive galaxies in the local group, Andromeda contains a wide variety of stars, ranging from young, hot stars to older, cooler stars. The stellar populations of galaxies like Andromeda provide a snapshot of their evolutionary history. By studying the ages, sizes, and compositions of stars in different parts of the galaxy, astronomers can learn about the processes that have shaped Andromeda over time. In particular, the central region of Andromeda contains a dense concentration of older stars, many of which are red giants, or white dwarfs. These stars are remnants of an earlier era in the galaxy's history, and they offer valuable insights into the galaxy's past. The outer regions of Andromeda, on the other hand, are home to younger, hotter stars, many of which are part of active star-forming regions. These stars are born in dense clouds of gas and dust, and their formation is influenced by the galaxy's environment and interactions with other galaxies. One of the most fascinating phenomena in Andromeda is its active star formation. Throughout the galaxy, particularly in its spiral arms, massive clouds of gas and dust are collapsing under their own gravity, giving birth to new stars. This process of star formation is ongoing and is one of the key drivers of the galaxy's evolution. The formation of new stars contributes to the galaxy's overall light and energy output, and the birth of massive stars leads to the creation of heavy elements that are later dispersed into the galaxy's interstellar medium when these stars die. Some of the most spectacular star-forming regions in Andromeda are found in its spiral arms, where the density of gas and dust is high. These regions are home to some of the brightest and most massive stars in the galaxy. Over time, these stars will evolve into supernovae, releasing enormous amounts of energy and enriching the galaxy with new elements. The remnants of these supernovae, such as neutron stars and black holes, will continue to shape the galaxy long after the stars themselves have died. The dynamics of star formation in Andromeda are also influenced by the galaxy's interactions with its neighbors. As Andromeda moves through the local group, its gravitational interactions with other galaxies, particularly the Milky Way, can trigger bursts of star formation. These interactions compress gas clouds and trigger the collapse of new stars. The upcoming collision between Andromeda and the Milky Way will likely result in an intense period of star formation, as the gas and dust in both galaxies collide and interact. This burst of star creation will add to the already vast population of stars in Andromeda, and will likely give rise to new structures within the galaxy. The impact of the Andromeda-Milky Way collision is not limited to star formation. It will also affect the supermassive black holes at the centers of both galaxies. Both the Milky Way and Andromeda contain supermassive black holes, which are millions to billions of times more massive than our Sun. These black holes are thought to have formed early in the history of their respective galaxies, and they play a crucial role in their evolution. As the two galaxies collide, the supermassive black holes will eventually merge, creating a new, even more massive black hole. This process will release enormous amounts of energy in the form of gravitational waves, rippling through space-time and providing scientists with a unique opportunity to study these mysterious objects. Interestingly, the supermassive black holes in both the Milky Way and Andromeda are relatively quiescent at the moment, meaning they are not currently actively consuming large amounts of gas and emitting intense radiation. However, the upcoming collision could trigger a period of heightened activity, as the gas from both galaxies is funneled into the black holes. This process, known as active galactic nucleus (AGN) activity, could result in the release of powerful jets of radiation and particles from the centers of both galaxies. These jets would illuminate the surroundings and provide astronomers with a glimpse into the workings of supermassive black holes. As Andromeda continues to evolve, its future will be shaped by a combination of internal and external forces. The ongoing star formation, the growth of its supermassive black hole, and the interactions with its satellite galaxies and neighboring Milky Way all contribute to the galaxy's evolution. In the distant future, as the Milky Way and Andromeda merge, the combined galaxy will continue to change, forming new stars, absorbing gas from the surrounding intergalactic medium, and experiencing further interactions with other galaxies in the local group. The story of Andromeda, like that of every galaxy, is a story of constant change and evolution. From its formation billions of years ago to its current state as one of the most massive galaxies in the local group, Andromeda has experienced a remarkable journey through time. And its future, marked by the collision with the Milky Way and the eventual merging of the two galaxies, is just one more chapter in the ongoing saga of cosmic evolution. Studying Andromeda offers us a window into the processes that shape the universe. From the birth of stars to the formation of supermassive black holes, from the dance of galaxies and clusters to the mysteries of dark matter, Andromeda is a laboratory for understanding the fundamental forces that govern the cosmos. As we continue to learn about this magnificent galaxy, we gain not only insight into its history and future, but also into the broader story of the universe itself. As we move forward, we can take a closer look at the role that Andromeda plays within its cosmic neighborhood. This neighboring role extends far beyond just gravitational interactions with the Milky Way. It involves a complex web of relationships with other galaxies in the local group. The local group, a collection of over 50 galaxies, is primarily dominated by three large galaxies: the Milky Way, Andromeda, and the Triangulum Galaxy. Together, these galaxies make up about 90% of the mass in the local group. The Milky Way and Andromeda are by far the most massive of the group, and they exert significant gravitational influence on one another. These two galaxies have already started a slow, inevitable approach toward each other, a process that will culminate in a collision in roughly 4.5 billion years. But Andromeda's role in the local group doesn't stop there. Despite its massive size, Andromeda has a number of smaller satellite galaxies that orbit it. Some of these are much smaller than Andromeda itself, and are being slowly pulled into its gravitational influence. Over time, these smaller galaxies will be absorbed, their stars incorporated into Andromeda's greater mass. This type of galactic cannibalism is not unique to Andromeda. It's a process that can be seen throughout the universe, where larger galaxies grow by merging with and absorbing smaller ones. One of the more intriguing satellite galaxies of Andromeda is M32, a small elliptical galaxy that has been captured by Andromeda's gravity. M32 is unique because it contains an unusually high number of older stars, and its core is exceptionally dense, a feature that suggests it may have once been a larger spiral galaxy itself. Over billions of years, Andromeda's gravitational forces may have stripped away the outer stars of M32, reducing it to its current size. Another satellite galaxy is NGC 205, which is similar in size to M32 but with a slightly more spread-out structure. As these smaller galaxies orbit Andromeda, they create a fascinating cosmic ballet, with stars, gas, and dark matter continually shifting in response to gravitational interactions. Some of these satellite galaxies are in a slow process of being pulled apart, their stars being scattered into the larger galaxy. Others are already in a much more advanced stage of being consumed, with their stars having long been integrated into Andromeda's larger structure. While we may think of galaxies as isolated entities, Andromeda's interactions with its satellites serve as a reminder that galaxies are not solitary in the vastness of space. They are continually interacting with their neighbors, drawing in smaller galaxies, expelling gas, and undergoing violent collisions that reshape their forms. In fact, the collision with the Milky Way will be a pivotal moment in the evolution of the local group itself. As the two galaxies merge, not only will they create a new galactic structure, but their interaction will also impact the other galaxies in the group. Galaxies that are far off in the distance may have their trajectories altered, pulled toward the center of the new galaxy formed by the merger. Another important aspect of Andromeda's role in the universe is its interaction with the intergalactic medium. While galaxies like Andromeda are primarily composed of stars, gas, and dark matter, they are also immersed in a vast sea of hydrogen gas that fills the spaces between galaxies. This hydrogen gas, known as the intergalactic medium, IgM, is sparse but crucial to the overall dynamics of the universe. The IgM is thought to play a key role in the formation of galaxies, as it provides the raw material from which new stars are born. The interaction between Andromeda and the IgM is a fascinating one. As Andromeda moves through the IgM, it creates what is known as a galactic wind. This is a stream of gas that is expelled from the galaxy as a result of processes like supernova explosions, the energy released by active stars, and the intense gravitational forces at work. The galactic wind of Andromeda, however, is not just an expulsion of material. It also contributes to the recycling of gas. As gas is ejected, it mixes with the surrounding intergalactic medium, and over time, it can be drawn back into the galaxy during future star formation events. This cycle of gas exchange helps sustain the ongoing processes of star birth and death within the galaxy. The future of Andromeda, particularly in light of its upcoming merger with the Milky Way, is one of the most exciting areas of research in modern astronomy. The collision between the two galaxies will have a profound effect on the stars, gas, and dust that make up both systems. For the stars themselves, however, the collision will likely have little impact. Given the vast distances between individual stars, most stars will pass by one another without directly colliding. However, the gravitational forces at play will reshape the orbits of many stars, and some stars may be ejected into intergalactic space. Others may be funneled toward the newly formed galactic core, where they will eventually be consumed by the supermassive black hole that sits at the center of the merged galaxy. One of the most significant effects of the collision will be the merging of the supermassive black holes at the centers of the Milky Way and Andromeda. These black holes, which are already immense in size, will eventually merge into a single, even more massive black hole. The process of this merger will release enormous amounts of energy, primarily in the form of gravitational waves, which will ripple through space-time and provide astronomers with a unique opportunity to study the behavior of black holes in extreme conditions. This merger will also trigger bursts of radiation as gas and stars are funneled toward the new black hole, creating a brief but intense period of activity in the newly formed galaxy. While the merger between Andromeda and the Milky Way is still billions of years away, the effects of this cosmic event are already being observed. As we continue to study Andromeda and its neighboring galaxies, we gain more insight into the forces that shape the universe. These galactic interactions are part of a never-ending cycle of creation, destruction, and rebirth that has been ongoing since the birth of the universe itself. And as we look toward the distant future, the merger of these two great galaxies will mark the next chapter in the evolution of the cosmos. Andromeda is more than just a neighboring galaxy to the Milky Way. It is a living, breathing entity that is constantly evolving. It is a testament to the forces of gravity, star formation, galactic cannibalism, and cosmic interaction that govern the universe. From its active star-forming regions to the dark matter halo that surrounds it, from the stellar populations that populate its spiral arms to the quiet, powerful presence of its supermassive black hole, Andromeda is a fascinating and complex system. Its role in the larger context of the universe continues to evolve, and its future, intertwined with the Milky Way, will shape the cosmic landscape for billions of years to come. The future of Andromeda, as it merges with the Milky Way, will bring about a profound transformation in the cosmic landscape of the local group. This galactic collision won't be a quick event but rather an ongoing process that will span billions of years, each stage unfolding a new chapter in the saga of these two massive galaxies. While it's difficult to predict every aspect of what will happen, we can be sure that the consequences will be felt far beyond the two galaxies involved. The merger of Andromeda and the Milky Way will have an undeniable effect on the other galaxies in the local group. Even though galaxies like the Triangulum Galaxy and the smaller dwarf galaxies will not physically collide with the merging giants, their paths will undoubtedly be altered. The immense gravitational forces at play during the merger will disrupt the motion of these galaxies, pushing them either toward the new galaxy formed from the merger or sending them flying out of the local group entirely. Some of these galaxies may even be pulled into the newly merged galaxy, joining the growing collection of stars, gas, and dust that will eventually form a new, unified galactic structure. But what will the newly formed galaxy look like? The collision of Andromeda and the Milky Way is likely to produce an entirely new type of galaxy. Currently, both galaxies are spiral galaxies, with well-defined arms filled with stars, gas, and dust. After the collision, however, the structure of the resulting galaxy may change dramatically. It may no longer resemble a spiral at all. Instead, it could form an elliptical galaxy, with a central bulge of stars and a diffuse outer region. The spiral arms that currently define both Andromeda and the Milky Way could be disrupted or entirely destroyed, leaving behind a more irregular, less structured galaxy. Over time, the gravitational forces between the stars, gas, and dark matter will continue to work together, shaping the new galaxy into a stable form, though it will likely take billions of years before this process is complete. It's also important to consider the effect the merger will have on star formation. During the collision, the gravitational forces will trigger the compression of gas clouds, which will ignite new rounds of star formation. This burst of new stars will add to the growing stellar population of the newly formed galaxy. However, the collision will also lead to the disruption of many existing stars. Some will be sent on new orbits, while others may be ejected entirely from the galaxy, flung into intergalactic space. The merging of the galaxies will be a violent event for the interstellar medium as well, as gas and dust are compressed, heated, and disturbed. This process could lead to the creation of massive star-forming regions, where young, hot stars are born at an accelerated rate. The supermassive black holes at the centers of both the Milky Way and Andromeda will also play a crucial role in the merger. These black holes will eventually collide and merge into one even more massive black hole. The process of this merger will release vast amounts of energy in the form of gravitational waves, which will ripple through the fabric of space-time. This event will provide astronomers with a unique opportunity to study the physics of black holes in ways that are not currently possible. As the black holes merge, they will likely cause the surrounding gas and stars to be drawn toward the new, larger black hole. This process could result in a brief but intense burst of radiation, known as an active galactic nucleus, AGN, as the gas is heated to extreme temperatures before being consumed by the black hole. While the stars themselves may not collide directly during the merger, the gas and dust clouds that populate the galaxies will interact in more violent ways. The collision will likely lead to the creation of new structures within the galaxy, including star-forming nebulae, stellar nurseries, and perhaps even new types of interstellar clouds. The resulting galaxy will be a far more complex and chaotic place than either the Milky Way or Andromeda ever was on their own. Beyond the immediate aftermath of the merger, there are deeper, long-term questions about the evolution of the new galaxy. Will it continue to form new stars at a rapid rate, or will the process eventually slow down as the available gas is used up? Will it become a quiet, old galaxy populated mainly by aging stars, or will it continue to thrive with fresh bursts of star formation for billions of years? These are questions that will require astronomers to continue studying the merger and its effects over vast stretches of time. The resulting galaxy, whatever its form, will be a testament to the incredible forces of gravity and energy that govern the universe. One of the other fascinating aspects of the Andromeda-Milky Way merger is the impact it will have on our own solar system. While the collision between the two galaxies will not directly cause the Sun to collide with another star, it will have a significant impact on the solar system's orbit. The gravitational forces of the merging galaxies will cause stars and other objects in the galaxy to shift their positions, and it's likely that the solar system's trajectory will change as a result. In the worst-case scenario, our solar system could be ejected from the galaxy, sent into deep intergalactic space. In a more moderate scenario, the solar system might simply be displaced within the new galaxy, but it would still be subject to the gravitational forces of the new galactic center. What is clear, however, is that the solar system will eventually be impacted by the shifting dynamics of the galaxy. Even though this event is billions of years away, the eventual movement of our solar system in the wake of the merger is an example of how dynamic and interconnected the universe is. Nothing in the cosmos is truly static, and even the most distant systems are subject to the forces of cosmic evolution. Beyond the physical changes, the merger of Andromeda and the Milky Way could also have an impact on the potential for life in the galaxy. While the collision won't directly affect planets or stars in the way we might imagine a catastrophic event, the change in the environment of the galaxy could alter the conditions necessary for life. For example, the increased radiation from the galactic center, the changes in cosmic rays, or the movements of the stars could all influence the stability of the planets that reside in the habitable zones of their stars. Furthermore, the loss of certain types of stars, such as red giants or massive, short-lived stars, could alter the types of elements that are abundant in the galaxy. Life, as we know it, is based on the elements created in stars, so shifts in the distribution of these elements could influence the future evolution of life in the galaxy. The process of star formation, which will continue in the aftermath of the merger, will also influence the types of planets that are formed and whether the conditions are right for life to take hold. In the grand scheme of things, the merger of Andromeda and the Milky Way will be just another chapter in the ongoing story of galactic evolution. It's a story that stretches back billions of years and will continue long into the future. The impact of this cosmic collision will be felt throughout the local group and beyond, shaping the galaxies that surround Andromeda and the Milky Way. And as we continue to study this event, we gain not only a deeper understanding of the forces that govern the universe but also a sense of the incredible scale and complexity of the cosmos. The study of the Andromeda-Milky Way merger is not only an exercise in understanding the evolution of two galaxies but also provides us with insight into the broader processes that shape the universe. These processes, galactic mergers, star formation, black hole dynamics, and the movement of dark matter, are all interconnected, influencing not just galaxies but the larger cosmic structure as well. Each merger, whether it involves two large galaxies like Andromeda and the Milky Way or smaller dwarf galaxies, leaves a distinct imprint on the cosmic landscape. These events are reminders of the ever-changing nature of the universe, where nothing is permanent, and everything is in a constant state of flux. As we look to the future, the Andromeda-Milky Way merger serves as a cosmic benchmark. It's a reminder of the inevitability of galactic evolution. For billions of years, these two galaxies have been on separate courses, each following its own cosmic journey, but they are now on a collision course, bound by gravity. In many ways, this merger represents the final chapter of their separate stories and the beginning of a new era, one where the familiar structure of the Milky Way and Andromeda will be replaced by something entirely different. This phenomenon also allows us to better understand the future of our galaxy and the possibilities for other civilizations that may exist, or may have existed, elsewhere in the universe. The merger's consequences on star formation, galactic structure, and the habitability of planets could influence the chances for life beyond Earth. If life is common in the universe, as some theories suggest, then understanding these large-scale galactic events is crucial to understanding where and how life might flourish in the future. Even beyond this, the merger provides a unique window into the dynamics of dark matter. Dark matter, which makes up a significant portion of the mass of galaxies but remains invisible to our current instruments, will play a key role in the merger. As galaxies collide and their gravitational fields interact, dark matter's influence will shape the way the galaxies evolve, merge, and ultimately settle into their final form. This mysterious substance, which we still don't fully understand, is a critical piece of the puzzle in understanding how galaxies form, grow, and interact with one another. While the details of the merger's aftermath are still to be revealed, one thing is certain: this event is going to drastically change the universe as we know it. It's a cosmic transformation that is, for all practical purposes, inevitable. The forces at work during this galactic collision are so immense that the scale of change it brings will be felt throughout the universe. Yet, it will be just one more chapter in the ongoing story of the cosmos, a story that continues to unfold over timescales that dwarf human lifespans. As we continue to observe Andromeda and the Milky Way from our vantage point on Earth, we are not just passive spectators. Every time we gaze into the night sky, we are looking into the future, a future where the paths of these two galaxies are forever intertwined. The collision that will occur billions of years from now is a reminder of how interconnected everything is in the universe. It's a reminder that no matter how vast the distances or how isolated individual objects might seem, they are all bound together by the forces of gravity and cosmic evolution. What's even more remarkable is that, despite the enormity of these events, they don't affect the individual lives of the stars or planets involved in the collision. Stars, in their vastness, are far enough apart that they are unlikely to collide directly with one another. Instead, they will interact on a larger scale, their paths and orbits altered by the gravitational forces at play. In a sense, the merger will be a reshaping of the galactic ecosystem, with stars and other celestial bodies shifting positions, forming new configurations, and perhaps even giving rise to entirely new kinds of astronomical phenomena. This cosmic reshaping will also have an impact on the interstellar medium, the vast expanse of gas, dust, and other particles that fills the space between stars. As galaxies collide, the gas clouds within them will be compressed, leading to new bursts of star formation. This process of stellar birth will be accompanied by the death of older stars, whose remnants may be flung into deep space or absorbed into the newly formed black holes at the galactic center. The cycle of birth and death in the universe is one of the most fundamental processes that shapes the cosmos. It's a constant reminder that even in the face of galactic mergers, life, as we understand it, is fleeting, and the stars, too, have their beginnings and ends. As the Andromeda Milky Way merger unfolds, it will create a new environment for stars to form and live out their life cycles. Some stars may shine brightly for billions of years, while others may be consumed by the new black hole that results from the merger. The process of star formation will continue in this newly merged galaxy, leading to the birth of new generations of stars, each with its own story to tell. In a way, the merging of Andromeda and the Milky Way is not just a cosmic collision, it's a cycle of rebirth. The collision will lay the groundwork for the next generation of stars and galaxies, and in turn, these stars will give rise to the next generation of planets and potential life. The universe, in all its vastness, operates on these cycles of creation, destruction, and transformation. It is through these cycles that new worlds are born, and new forms of life can emerge. As we continue to explore the universe and deepen our understanding of the forces that govern it, the Andromeda Milky Way merger will continue to be an area of fascination for astronomers, scientists, and anyone interested in the grand scale of cosmic evolution. The story of these two galaxies, their collision, and the aftermath will shape the future of the local group and offer invaluable insights into the broader processes of galactic evolution, star formation, and the ultimate fate of our universe. The most intriguing aspect of this story, perhaps, is the fact that it's happening on such an immense scale, one that spans billions of years. For humans, it may seem like an event that is far removed from our daily lives, but in truth, the merger will play a fundamental role in the future of our galaxy and the universe itself. Even as we face the uncertain future of Earth, the knowledge that the universe is always in motion, always evolving, is a reminder of the incredible vastness and beauty of the cosmos. And so, the story of Andromeda and the Milky Way continues to unfold. Though the collision may be billions of years away, its implications stretch far into the future. What happens when two galaxies collide? It's not just the stars that will change. The entire structure of the universe will be forever altered, and we, as observers of this cosmic drama, will continue to watch as the stars and galaxies weave their intricate stories. The merger of Andromeda and the Milky Way will leave its mark on the universe, a mark that will endure long after the collision itself has passed. The universe's constant state of flux is a reminder that even as we observe, learn, and grow, we are but a small part of a much larger picture. The Andromeda-Milky Way merger is just one chapter in the long and ongoing story of the cosmos, and as the universe continues to evolve, so too will our understanding of the forces at work in the vast reaches of space. As we look ahead to the distant future, one must ponder the legacy of this merger. While we won't be around to witness the dramatic events firsthand, it serves as a striking example of how galaxies are not fixed entities but rather dynamic structures, constantly changing and evolving. Each merger, each interaction between galaxies, represents an opportunity for growth, new creation, and the unfolding of new possibilities. In the grand timeline of the universe, the Andromeda-Milky Way collision will simply be another chapter, albeit an incredibly significant one. This merger holds lessons far beyond just the physical universe. It challenges the way we view time, scale, and existence itself. The scale of galactic events is so vast that it often seems incomprehensible. The thought that two galaxies, containing trillions of stars, can merge over billions of years, each star moving with a trajectory that we can barely comprehend, underscores the complexity of the universe. It forces us to confront the sheer scale of cosmic processes and our place within them. In our daily lives, we may feel small and insignificant, but when we take the long view of the cosmos, we realize that we are part of something much greater. The collision of Andromeda and the Milky Way will reshape not only the stars but also the very fabric of our galaxy. It will create new environments for planets and stars to form, potentially giving birth to new worlds that could host life. In a sense, these collisions are the ultimate creators, forging new stars, new solar systems, and new possibilities. Yet, it is also a reminder of the fragile nature of life itself. Just as the collision will result in the birth of new stars, it will also lead to the death of older ones. The lives of stars, just like the lives of organisms, are finite, and the universe constantly evolves, remakes, and reinvents itself. For those of us living on Earth today, it's easy to imagine that our solar system, our galaxy, and our world are permanent fixtures in the universe. However, the reality is that everything in the cosmos is in a state of constant change. The Andromeda-Milky Way merger is just one example of how galaxies are not static. They are dynamic, constantly interacting with each other, shaping and reshaping the fabric of the universe. And in this process, the universe reveals itself as a living, breathing organism, filled with energy, movement, and transformation. The merger will also have profound effects on the future of space exploration. While this event may be billions of years in the future, it will inform how we approach the study of the cosmos in the present day. Understanding the mechanics of galactic mergers, star formation, and the role of dark matter will help us make sense of the larger universe in which we live. And, as we continue to explore space, the lessons from the Andromeda-Milky Way merger will serve as a key reference point for astronomers and astrophysicists in their ongoing efforts to map out the forces that shape the cosmos. In terms of technology, our study of such cosmic events might push the boundaries of what is possible. As we develop more sophisticated telescopes and observatories, our understanding of galactic dynamics will only deepen. We may eventually discover new ways to measure gravitational waves, dark matter, and other fundamental forces that are involved in such grand cosmic collisions. These advancements will not only deepen our understanding of the universe but could also have far-reaching applications for our own technological progress. What we learn from the study of Andromeda's eventual merger with the Milky Way may one day lead to new breakthroughs in energy, physics, and even space travel. Moreover, the merger will be a reminder of the delicate balance between order and chaos that governs the universe. While the gravitational forces between the two galaxies are immense, and the energy released during the collision will be staggering, these forces are ultimately a part of the cosmic dance that has been occurring for billions of years. Stars are born and die, galaxies collide and merge, and new structures are created. The cosmos operates not through chaos alone, but through a delicate interplay of forces, some predictable, others random. In this way, the Andromeda-Milky Way merger is just another part of this cosmic cycle, one that continues to unfold over vast periods of time. This sense of cosmic interconnectedness extends beyond galaxies and stars. It resonates deeply with our understanding of the universe as a whole. The study of such grand cosmic events is not just an exercise in scientific inquiry, it's a philosophical one as well. What is the nature of the universe? How do we fit into this vast and complex system? The Andromeda-Milky Way merger challenges us to think beyond the constraints of our daily lives and to consider our place within the larger cosmic context. It pushes us to think not just about the present moment, but about the future of the universe and the legacy of all that came before. As we contemplate these questions, we must also confront the idea that the universe is not just a place of matter and energy, but a space that holds the potential for discovery, understanding, and exploration. For those of us living on Earth, the Andromeda-Milky Way merger offers a glimpse into the incredible potential for future scientific and technological achievements. Our exploration of the cosmos, through both theoretical study and practical missions, will continue to evolve. And as we look to the stars, we will find not just new frontiers but also a deeper understanding of ourselves and our place in this vast, interconnected universe. While we may never live to see the Andromeda-Milky Way merger unfold, it remains one of the most awe-inspiring events in the future of our galaxy and the universe at large. It's a story that reminds us of the fragility of time, the beauty of cosmic transformation, and the endless potential for discovery. The galaxies are on a path that will forever change their structure and the stars within them, and we, as part of this cosmic tapestry, continue to learn, adapt, and grow in our understanding of the universe. The Andromeda-Milky Way merger is, in many ways, a symbol of the vastness and interconnectedness of everything in existence, and it's a reminder that the universe is always in motion, always evolving, and always waiting for us to discover what comes next. The Andromeda-Milky Way collision is a cosmic event that, though it might seem distant in both time and space, serves as a reminder of just how interconnected the universe truly is. Our galaxy, the Milky Way, along with its soon-to-be neighbor, the Andromeda Galaxy, exists in an intricate web of celestial bodies, all orbiting, colliding, and evolving over unimaginable timescales. It's a humbling thought that everything we see in the night sky is moving, transforming, and shaping one another in ways that can only be described as majestic. In fact, the study of these cosmic events, like the eventual Andromeda-Milky Way merger, is also a study of the grand, natural processes that have been occurring since the dawn of time. For billions of years, galaxies have been interacting with each other, growing larger and more complex, as their stars and planets evolve. Our understanding of this cosmic dance is continuously evolving, and with each new discovery, we come closer to understanding the universe not just as a physical place but as a dynamic, ever-changing reality. One of the remarkable aspects of this merger is how it shows that galaxies are not just static collections of stars. They are dynamic, living entities in their own right, constantly changing. This merging process will give birth to new stars and might even lead to the formation of a completely new galaxy, an entirely new structure in the universe. The idea that this cosmic event is just another part of a larger cycle of life and death in the universe is both awe-inspiring and humbling. In terms of galactic evolution, the merger of Andromeda and the Milky Way offers us a glimpse into how galaxies form, evolve, and interact over time. As these two massive galaxies come together, they will trigger new cycles of star formation. The shockwaves from the collision will compress gas clouds, which in turn will lead to the birth of new stars. These stars, while being created in the heart of a cosmic collision, could end up in completely different parts of the new, merged galaxy. And it is here, amidst the birth of new stellar systems, that planets, moons, and other celestial bodies will form, some of which may even harbor the potential for life. While the star-forming activity of this merger is undoubtedly exciting, it also emphasizes the inevitability of cosmic change. Nothing in the universe is permanent, and the fact that we are able to observe such an incredible event, even from our distant position on Earth, underscores how fleeting everything truly is. For humanity, this event serves as a cosmic reminder that our own existence, both as individuals and as a species, is part of a much larger, ever-evolving process. This realization challenges us to think about our place in the cosmos. For centuries, we've been focused on the here and now, on the problems that affect us on Earth: climate change, conflict, technology, and exploration. But when we look up at the stars and think about the galaxies beyond, we are reminded that our world, our galaxy, and even our solar system are small parts of something much greater. We are just one thread in the vast tapestry of the universe. Our current understanding of the cosmos is still in its infancy, and as we continue to explore and learn, new questions will arise. How will humanity respond to the challenges posed by this greater universe? Will we be able to adapt to the rapid changes, like the upcoming merger between Andromeda and the Milky Way, or will we simply be spectators in the vast drama of the cosmos? Perhaps this is one of the most profound lessons from the Andromeda-Milky Way merger. It forces us to consider the nature of time and existence. In the grand scheme of the universe, we are but a fleeting moment. Our lives, our planet, and even our galaxy exist for only a short time on the cosmic scale. The merger of two galaxies billions of years in the making reminds us that time moves far beyond the span of human history, and yet we are here, in this moment, able to witness a tiny sliver of this endless progression. The very fact that we are aware of the future of our galaxy, that we can contemplate events that will take place in billions of years, speaks to the extraordinary nature of human curiosity and achievement. At the same time, this cosmic collision invites us to consider the unknowns that lie ahead. What mysteries are still hidden within the depths of space? What new discoveries will the merger of Andromeda and the Milky Way reveal? Even as we gaze back through time, into the formation of galaxies, we can't help but wonder what is yet to come. How will the merger affect the future of life in our galaxy, if life still exists then? What will the new galaxy, formed from the merger of two great cosmic entities, look like? Will it be a peaceful haven for new stars to flourish, or will it be a chaotic, turbulent environment where only the strongest stars survive? The collision of Andromeda and the Milky Way is not only a study in galactic mechanics but a metaphor for the cyclical nature of life itself. As galaxies collide and form new structures, they offer us a glimpse into our own existence, full of turbulence, change, and rebirth. Life, like the cosmos, is in constant flux. We, too, will face moments of dramatic change, but those moments can lead to the creation of something new, something better, something that pushes us forward into an unknown and exciting future. It's easy to feel small when you think about events on a cosmic scale, but the study of these events also reveals the incredible potential of human discovery. Every new piece of knowledge we gain about the universe opens up further questions and possibilities, much like how each collision of galaxies leads to new formations of stars and cosmic phenomena. Our understanding of the universe, much like the Andromeda-Milky Way merger itself, is just one stage in a larger cycle, and it's up to us to continue pushing the boundaries of what we know. This is the essence of space exploration and scientific inquiry, to look beyond the horizon and ask the questions that will shape the future of humanity. And as we continue to study the Andromeda Galaxy, the Milky Way, and their eventual collision, we are reminded that the universe is vast, mysterious, and full of potential. Each discovery brings us closer to understanding our place in the cosmos, and each new piece of knowledge shapes the next chapter of this extraordinary, ever-evolving journey. The merger of Andromeda and the Milky Way is not just a moment in cosmic history. It's a reminder that everything is connected, that galaxies, stars, planets, and even life itself are part of a larger cosmic system. And just as these two galaxies will collide and give birth to new stars and new possibilities, so too does humanity continue to evolve, grow, and discover new frontiers. The future is unwritten, and as we continue to explore the mysteries of space, we become part of the ongoing story of the universe. And who knows what lies ahead as we move forward into the unknown, propelled by our curiosity and the desire to understand the cosmos in all its vast, awe-inspiring glory. As we venture deeper into the cosmic story, it's important to reflect on the journey that got us here. The Andromeda Galaxy, for all its grandeur and mystery, wasn't always understood the way it is today. Throughout human history, our view of the cosmos was limited, confined to the stars we could see with the naked eye. It wasn't until the advent of modern telescopes and scientific instruments that we began to unravel the complexities of distant galaxies, including Andromeda. In the early days, Andromeda was merely a smudge in the night sky, a faint glow that early astronomers had trouble understanding. Ancient civilizations observed it, but without the knowledge and technology to investigate it more thoroughly, they could only speculate about what it was. Some even thought it was a nebula, a cloud of gas and dust, while others believed it was part of our own Milky Way galaxy. It wasn't until the early 20th century that we began to comprehend the true scale of what we were looking at. The work of astronomers like Edwin Hubble would forever change our understanding of the universe. Hubble's observations and the subsequent discovery of the expanding universe led to the realization that galaxies, like Andromeda, were not just distant stars within the Milky Way but entirely separate galaxies in their own right. This was a revolutionary idea, one that fundamentally changed our understanding of the cosmos. Instead of being the center of everything, Earth was just one tiny speck in a universe filled with countless galaxies, each with its own stars, planets, and mysteries. Hubble's discovery that Andromeda was a separate galaxy helped propel the field of cosmology forward. From that moment on, astronomers began to view galaxies as individual entities, each with its own unique characteristics. Andromeda, in particular, stood out as one of the closest galaxies to the Milky Way, making it an ideal candidate for study. The more we learned about Andromeda, the more we realized how much it resembled our own galaxy, both in structure and in the stars it contained. Today, Andromeda is known to be a spiral galaxy, much like the Milky Way. It's home to an estimated 1 trillion stars, more than twice the number in our own galaxy. Its size is immense, with a diameter of roughly 220,000 light-years, making it the largest galaxy in our local group. Despite its size, however, Andromeda's true beauty lies in the fact that it is a dynamic, living entity evolving with time. As previously mentioned, its eventual merger with the Milky Way is not a catastrophe but part of a larger cosmic process. And while the thought of two galaxies colliding might seem chaotic, the outcome will be a new galactic structure, a beautiful fusion of stars, gas, and dust that will continue to evolve long after the merger has taken place. But even before that grand collision, Andromeda has provided a wealth of knowledge about the life cycle of galaxies. Studying its spiral arms, its central bulge, and its various star populations gives us insight into the processes that govern galactic formation and evolution. The study of Andromeda's stars, for example, has allowed astronomers to estimate the age of the galaxy, revealing that it is roughly 10 billion years old, roughly the same age as the Milky Way. This places both galaxies at the heart of the cosmic evolutionary timeline, highlighting their roles in the larger story of the universe. One of the most fascinating aspects of Andromeda is its dark matter. Like the Milky Way, Andromeda is surrounded by a halo of dark matter, an invisible substance that makes up much of the galaxy's mass. Although we can't see dark matter directly, its presence is inferred through its gravitational effects on visible matter. The discovery of dark matter in galaxies like Andromeda has revolutionized our understanding of the universe, revealing that much of the cosmos is made up of matter that we cannot directly detect. This mysterious substance remains one of the most profound puzzles in modern astrophysics, and Andromeda's dark matter halo offers valuable clues as to how this elusive substance behaves. In addition to dark matter, Andromeda is also home to a fascinating array of stellar phenomena. It contains star-forming regions, where new stars are being born from clouds of gas and dust, as well as older, dying stars in its outer regions. These stars are part of the complex life cycle of a galaxy, where stars are born, live, and eventually die, releasing new elements into the interstellar medium. Andromeda, like the Milky Way, is a galaxy that is constantly evolving, with new stars forming and old stars fading away in a never-ending cycle. But perhaps one of the most intriguing aspects of Andromeda is the discovery of its satellite galaxies. These smaller galaxies orbit Andromeda, much like the Milky Way's satellite galaxies orbit our galaxy. These include the M32, M110, and NGC 185, among others. These satellite galaxies provide valuable insights into the interactions between galaxies, showing how smaller galaxies can be absorbed and assimilated into larger galaxies over time. It's believed that some of Andromeda's satellite galaxies were once independent but were gradually drawn into the larger galaxy's gravitational field. This process of galactic cannibalism is thought to be a common occurrence in the universe, with larger galaxies steadily absorbing smaller ones, growing ever more massive in the process. These satellite galaxies also provide a unique window into the past. By studying their stars and their interaction with Andromeda, astronomers can learn about the early history of the universe, including the formation of the first galaxies and the processes that led to the creation of the galaxies we see today. This is one of the reasons why Andromeda is such a valuable target for astronomers. Its history is a microcosm of the larger cosmic story, and by studying it, we can better understand the forces that shape the universe as a whole. As we look forward to the eventual collision between Andromeda and the Milky Way, it's easy to get caught up in the drama of the event. However, it's important to remember that this collision, like the rest of the universe, is part of a natural process of change and evolution. The Andromeda-Milky Way merger will not be an instantaneous event. Rather, it will take billions of years for the two galaxies to fully merge. This long, drawn-out process will involve countless interactions between stars, gas, and dust, with some stars being flung into new orbits and others colliding to form new, larger stellar systems. As the merger progresses, new questions will arise. How will the gas clouds that fuel star formation in both galaxies interact? Will the supermassive black holes at the centers of both galaxies collide, creating a new, even larger black hole? And perhaps most importantly, how will life, if it exists in the future, adapt to these massive changes in the galaxy? Will intelligent civilizations, if they have risen by then, be able to survive the cosmic upheaval? These questions underscore the wonder and mystery of the universe. The Andromeda-Milky Way collision, while a predictable event in the grand scheme of things, is still a deeply fascinating and mysterious occurrence. It forces us to consider not only the future of our galaxy but also the larger questions of cosmic evolution, dark matter, and the very nature of the universe itself. As we continue to explore the cosmos, Andromeda stands as a testament to the vastness of space and the ever-evolving nature of the universe, a reminder that even the most stable and familiar structures in the cosmos are not immune to the forces of change. As we continue our exploration of the Andromeda Galaxy, it's essential to delve into the many aspects of its composition and dynamics that make it a key player in the universe's ongoing story. We've discussed its vast size, its spiral shape, and its eventual collision with the Milky Way, but there are many more fascinating details about Andromeda that reveal the complexity and beauty of this galaxy. From its stellar populations to the mysteries of its supermassive black hole, Andromeda offers a treasure trove of astronomical phenomena to study, and each discovery brings us closer to understanding not only our galaxy but the entire cosmos. One of the most remarkable features of Andromeda is its stellar populations. Just as the Milky Way contains stars of various ages and types, Andromeda hosts a diverse array of stars. The galaxy's stars are organized into several distinct groups, each with its own characteristics and history. At the heart of Andromeda lies a dense concentration of older stars, many of which have been around for billions of years. These stars form the bulge of the galaxy and are primarily red giants and other older stellar types that have evolved beyond their main sequence phase. The outer regions of the galaxy, however, are home to a much younger population of stars, particularly in the spiral arms. These regions are rich in gas and dust, the essential ingredients for star formation, and they give rise to massive, hot stars that burn brightly in the ultraviolet spectrum. These young stars contribute to the overall energy output of the galaxy, and their intense radiation can ionize the surrounding gas, creating nebulae and star-forming regions. One of the most famous star-forming regions in Andromeda is the NGC 206, a large and bright nebula that is a cradle for new stars. As we study Andromeda's stellar populations, we also learn about the chemical evolution of galaxies. The stars in the outer regions of Andromeda are enriched in heavier elements compared to the older stars in the bulge. This reflects the ongoing process of stellar nucleosynthesis, where elements such as carbon, oxygen, and iron are created in the cores of stars and then dispersed into the interstellar medium when those stars die. Over time, as more stars are born and die, the galaxy becomes richer in these heavier elements, a process known as chemical enrichment. Andromeda, like the Milky Way, has undergone this process over billions of years, and its stars are now composed of a mixture of old and new elements. At the very center of Andromeda lies an extraordinary object that has captivated astronomers for decades, its supermassive black hole. Like the Milky Way, Andromeda contains a black hole with a mass millions of times that of the Sun. This black hole, known as M31*, is located at the galaxy's core and exerts a powerful gravitational influence on the surrounding stars and gas. Observations of stars orbiting the center of Andromeda suggest that the black hole is actively pulling in material, creating an accretion disk that emits X-rays and other high-energy radiation. While we cannot see the black hole itself, its presence is confirmed through its effect on nearby objects. The study of Andromeda's supermassive black hole offers valuable insights into the role these enigmatic objects play in the evolution of galaxies. Supermassive black holes are thought to be present at the centers of most large galaxies, and they may play a key role in regulating the growth of the galaxy. Some theories suggest that the energy released by the accretion of material into the black hole could limit the amount of gas available for star formation, thereby controlling the rate of star birth. This feedback mechanism could explain why galaxies like Andromeda have ceased forming new stars at the rapid rate they once did, transitioning from a star-forming galaxy to one that is more stable. Beyond the black hole, Andromeda also has a complex system of globular clusters. These dense clusters of stars, which can contain hundreds of thousands of stars packed into a small region of space, are found throughout the galaxy. Some of these globular clusters orbit the central bulge, while others are located in the outskirts of the galaxy. The study of these clusters provides a glimpse into the early history of Andromeda, as many of them are thought to be some of the oldest structures in the galaxy. These clusters are remnants from the galaxy's early days and can help astronomers learn about the conditions that existed in the universe billions of years ago. The globular clusters in Andromeda are not only important for understanding the galaxy's past but also for studying the nature of dark matter. These clusters are thought to be embedded in dark matter halos, and their motion can reveal clues about the distribution and properties of dark matter in the galaxy. The relationship between dark matter and the visible matter in Andromeda is a topic of intense study, as it could provide answers to some of the most fundamental questions in astrophysics. How much of the galaxy's mass is made up of dark matter? How does dark matter interact with regular matter? These are questions that Andromeda, with its relatively well-studied structure, can help answer. As we shift our focus to the interactions between Andromeda and its neighboring galaxies, it becomes clear that the galaxy is part of a dynamic and complex system. Andromeda is the largest galaxy in the local group, a collection of more than 50 galaxies that includes the Milky Way, the Triangulum Galaxy, and many smaller dwarf galaxies. The local group is bound together by gravity, and the galaxies within it are constantly interacting, exchanging gas, stars, and even entire galaxies in some cases. One of the most important interactions within the local group is the ongoing gravitational tug-of-war between Andromeda and the Milky Way. As we've already discussed, these two galaxies are on a collision course, and their eventual merger will have profound consequences for both galaxies. However, this is far from the only interaction in the local group. Andromeda has several satellite galaxies that orbit it, and these galaxies are slowly being pulled into Andromeda's gravitational field. Some of these satellite galaxies are on the verge of being absorbed by Andromeda, while others are in the process of merging with the larger galaxy. One of Andromeda's most famous satellite galaxies is the M32, a small elliptical galaxy that orbits the Andromeda Galaxy. M32 is unique in that it has a very high concentration of stars in its central region, but it lacks the extended outer regions that are typical of most elliptical galaxies. This has led astronomers to hypothesize that M32 may have once been a larger galaxy that was stripped of its outer regions as it was pulled into Andromeda's gravitational field. The study of M32 and other satellite galaxies offers valuable insight into the processes of galactic cannibalism, where larger galaxies absorb smaller ones over time. The Triangulum Galaxy, another member of the local group, is also a key player in the gravitational interactions of Andromeda. The Triangulum Galaxy, also known as M33, is the third largest galaxy in the local group and is gravitationally bound to both Andromeda and the Milky Way. While it is much smaller than Andromeda, it is still a massive galaxy in its own right, with its own population of stars, gas, and dust. The future of the Triangulum Galaxy is uncertain, but it is likely to be affected by the collision between Andromeda and the Milky Way. As the two larger galaxies merge, the Triangulum Galaxy may be drawn into the interaction, either merging with one of the two or being stripped of its stars and gas. In addition to these gravitational interactions, Andromeda is also undergoing a process of internal evolution. Like the Milky Way, Andromeda is home to a wide range of stellar populations, each with its own unique characteristics. The galaxy is constantly evolving as new stars are born and old stars die, and these processes have a significant impact on the galaxy's overall structure. For example, the rate of star formation in Andromeda has been declining over the past few billion years, and the galaxy is now in a more stable phase of its life cycle. This decline in star formation is thought to be due to a combination of factors, including the consumption of available gas by the central black hole and the ongoing gravitational interactions with nearby galaxies. Despite the eventual merger between Andromeda and the Milky Way, both galaxies will continue to evolve and change in the meantime. New stars will continue to form, old stars will continue to die, and the dynamic forces of gravity will continue to shape the galaxies in ways we can only begin to understand. The future of Andromeda is written in the stars, and as we observe its evolution, we gain a deeper understanding of the fundamental processes that drive the universe. As we continue our exploration of Andromeda, it's important to shift our focus to the galaxy's ongoing interaction with its environment and how this shapes its future. The Andromeda Galaxy is not isolated in the vastness of space. It is part of the gravitationally bound local group, a collection of galaxies that includes the Milky Way, the Triangulum Galaxy, M33, and several smaller dwarf galaxies. The interactions between these galaxies are not only shaping their individual structures but also influencing the large-scale structure of the universe. As we have already discussed, Andromeda's future collision with the Milky Way will alter both galaxies, but there are many other intriguing dynamics happening around it that deserve further exploration. The local group, while it may seem like a relatively small region in the cosmos, is a hub of galactic interaction. Andromeda, with its massive size, is the largest member of this group, but it is not alone in its interactions. The gravitational forces at play within the group are constantly pulling on the galaxies, causing them to move toward one another over vast timescales. This gravitational dance affects not only the individual galaxies but also their star systems, dark matter halos, and gas clouds. As we've seen with galaxies like the Triangulum Galaxy and M32, these interactions are not always smooth. In fact, many of the smaller galaxies in the local group are slowly being consumed by their larger neighbors. Over time, their stars and gas are either absorbed into the larger galaxies or flung out into the space between galaxies. This process, known as galactic cannibalism, is a natural part of galaxy evolution, and Andromeda is no exception. It has been steadily pulling in and consuming its satellite galaxies for billions of years. One of the key aspects of Andromeda's future is its interaction with the Milky Way. As we've previously mentioned, Andromeda and the Milky Way are on a collision course, and in about 4.5 billion years, the two galaxies will collide and begin to merge. This is not an unusual event in the universe. In fact, most large galaxies have experienced mergers with smaller galaxies throughout their lifetimes, and many are still in the process of merging. These mergers can trigger bursts of star formation as gas clouds collide and compress, but they can also lead to the stripping away of stars and gas from both galaxies. The eventual merger between Andromeda and the Milky Way will likely reshape both galaxies entirely. The process will take place over billions of years, and in the end, the two galaxies will merge into a single, more massive elliptical galaxy. The supermassive black holes at the centers of both galaxies will likely also merge, creating an even more massive black hole at the heart of the new galaxy. This new black hole will have an even stronger gravitational pull, affecting the orbits of stars and other objects within the merged galaxy. The new elliptical galaxy that emerges from this merger will likely have a much different structure than either Andromeda or the Milky Way do today. Its spiral arms will be lost, and it will become a more rounded, featureless galaxy, populated by older stars and remnants from the merger. However, this process is not just limited to the Milky Way and Andromeda. The Triangulum galaxy, M33, is also involved in the gravitational dance of the local group. While it is much smaller than Andromeda and the Milky Way, Triangulum is still a significant player in the group. The gravitational interactions between Triangulum and the other two galaxies are complex, and it's possible that Triangulum could be pulled into the merging galaxies over time, either by being absorbed into one of them or by being flung out into intergalactic space. The fate of Triangulum, like many smaller galaxies, will be shaped by the larger gravitational forces at play in the local group. The future of Andromeda and the Milky Way is a powerful reminder of the dynamic and ever-changing nature of the universe. Galaxies are not static objects. They are constantly evolving, growing, merging, and dying. In the case of Andromeda, its collision with the Milky Way will mark a pivotal moment in its history, but it will not be the end of the story. The combined galaxy will continue to evolve, and its stars will continue to burn and die, creating new generations of elements and enriching the interstellar medium with each generation. But there is more to Andromeda than its interactions with other galaxies. The galaxy is home to a variety of interesting and mysterious objects, from its supermassive black hole to its globular clusters, each of which has its own story to tell. The study of these objects helps astronomers unravel the mysteries of galaxy formation and evolution. Globular clusters, in particular, are a fascinating aspect of Andromeda's structure. These dense, spherical collections of stars are some of the oldest structures in the galaxy, and studying them provides a glimpse into the early history of both Andromeda and the universe itself. Globular clusters are thought to be remnants of the earliest stages of galaxy formation. They contain some of the oldest stars in Andromeda, many of which are believed to be more than 10 billion years old. These ancient stars offer important clues about the conditions that existed in the early universe, including the first generation of elements that formed after the Big Bang. Studying the globular clusters in Andromeda allows astronomers to understand the chemical evolution of the galaxy and gain insights into the processes that led to the formation of its more complex stellar populations. Beyond the stars, Andromeda also contains a vast amount of gas and dust, much of which is involved in the process of star formation. The spiral arms of the galaxy are rich in these raw materials, and they serve as the birthplaces for new stars. This ongoing process of star formation is one of the factors that makes Andromeda such a dynamic and evolving galaxy. However, the rate of star formation has been steadily decreasing over the past few billion years, as the available gas is used up and the central black hole continues to consume material. This shift from a star-forming galaxy to a more stable, passive galaxy is a common trend seen in many larger galaxies, and it provides valuable insights into the life cycle of galaxies as a whole. Andromeda is also home to a variety of interesting phenomena, such as its vast dark matter halo. Like the Milky Way, Andromeda is surrounded by a massive halo of dark matter, a mysterious substance that does not emit light but exerts a strong gravitational pull on the visible matter in the galaxy. The study of dark matter is one of the most exciting areas of modern astronomy, as it holds the key to understanding many of the fundamental forces of the universe. Dark matter is thought to make up a significant portion of the total mass of galaxies, yet its exact nature remains one of the biggest unsolved mysteries in science. The presence of dark matter in Andromeda can be inferred from the motion of stars and gas within the galaxy. If only visible matter were present, the galaxy's stars would move much more slowly than they actually do. Instead, the star's high velocity suggests that there is a large amount of invisible mass exerting a gravitational pull on them. This mass is thought to be dark matter, although its exact properties remain elusive. Studying the distribution and behavior of dark matter in Andromeda is helping astronomers understand the nature of this mysterious substance and its role in the formation and evolution of galaxies. As we consider the future of Andromeda, it's clear that it will continue to be a subject of intense study and fascination for astronomers and astrophysicists alike. Whether it's exploring the galaxy's supermassive black hole, its complex interactions with neighboring galaxies, or its mysterious dark matter halo, there is always something new to learn about this remarkable galaxy. The Andromeda Galaxy is a living, breathing entity in the cosmos, constantly evolving and changing as it interacts with the universe around it. And as we continue to observe and study Andromeda, we gain deeper insights into the very nature of the universe itself. As we continue our deep dive into the Andromeda Galaxy, it's important to touch upon the broader significance of this galaxy in the context of the universe itself. Not only is Andromeda one of the most studied galaxies due to its proximity and size, but it also serves as a kind of mirror, reflecting the processes and phenomena occurring in other galaxies across the cosmos. Andromeda, like the Milky Way, is an example of a spiral galaxy, a common galaxy type that accounts for a significant portion of the universe's galaxy population. Studying Andromeda provides essential insights into the formation, evolution, and eventual fate of galaxies of similar structure and mass. Looking at Andromeda's place in the universe, we can better understand the life cycle of galaxies. Spiral galaxies like Andromeda are thought to form from clouds of gas and dust that collapse under their own gravity. Over time, these clouds of gas condense into stars, and the stars begin to orbit a central region, forming the familiar spiral arms. The galaxy's structure, characterized by its disk of stars and gas, as well as a central bulge and surrounding halo of stars and dark matter, is a result of billions of years of evolution. This process is not unique to Andromeda. It's a model that applies to many galaxies throughout the universe, though the specifics of each galaxy's formation are shaped by its individual conditions. In terms of its long-term evolution, the Andromeda Galaxy is already showing signs of slowing down in its star formation processes. The rate of new star formation in Andromeda has been decreasing for billions of years, and this trend is expected to continue. This is due in part to the depletion of the gas needed to fuel new stars. However, Andromeda is not dead by any means. It still contains vast amounts of gas in its spiral arms, and smaller star-forming regions continue to dot the galaxy. Still, the galaxy's overall star formation rate is dropping, and it's likely that, in the distant future, the galaxy will become a more passive, quiescent galaxy, like many older elliptical galaxies. Interestingly, the end of star formation in a galaxy like Andromeda doesn't mean the end of its activity. The galaxy will still have stars burning in its core for billions of years, and new stars will occasionally form from the remaining gas. Over time, however, the galaxy's stars will grow older, and the galaxy will become populated primarily by older, redder stars. This process is often referred to as galactic quenching, and it's something that is observed in many large galaxies as they age. Once star formation slows down, galaxies enter a period of relative stability, during which they continue to evolve slowly, primarily through the interaction of stars and the gravitational pull of their central black hole. The supermassive black hole at the heart of Andromeda is an intriguing feature of the galaxy that continues to captivate scientists. Located in the galactic center, this black hole, known as M31*, is incredibly massive, with a mass equivalent to billions of times that of our Sun. Its gravitational pull dominates the central region of the galaxy, influencing the orbits of stars and gas around it. Supermassive black holes like M31* are thought to be a common feature in the centers of most large galaxies, including the Milky Way. M31* has a significant impact on the evolution of Andromeda. As we mentioned earlier, the merger between Andromeda and the Milky Way will likely involve the merging of the two supermassive black holes at the centers of each galaxy. This process, which will take place over billions of years, will lead to the formation of an even larger black hole, likely one of the largest known to exist. The intense gravitational forces at work in such a merger will likely result in the release of immense amounts of energy, including gravitational waves, as the two black holes spiral toward each other before merging. In addition to its central black hole, Andromeda is also home to a wide variety of other interesting and important phenomena. One of these is the presence of globular clusters, dense spherical collections of stars that orbit the galaxy's center. Globular clusters are some of the oldest structures in the galaxy, containing stars that are more than 10 billion years old. These ancient clusters provide valuable insights into the early history of Andromeda and the universe as a whole. Studying these clusters helps astronomers understand the conditions that existed in the early stages of galaxy formation. The globular clusters in Andromeda are especially interesting because they are thought to have formed during the galaxy's early history, possibly as a result of mergers with smaller galaxies. Some of these clusters may even predate the formation of Andromeda itself, having been part of smaller galaxies that were later absorbed by Andromeda as it grew over time. Studying the stellar populations in these globular clusters allows astronomers to trace the galaxy's history and understand how it evolved over billions of years. Another fascinating aspect of Andromeda is its dark matter halo. Dark matter, which makes up a large portion of the galaxy's total mass, cannot be seen directly, as it does not emit or reflect light. However, its presence can be inferred by its gravitational effects on visible matter. The dark matter halo surrounding Andromeda extends far beyond the galaxy's visible stars and gas, and its distribution plays a crucial role in the galaxy's overall structure and dynamics. Dark matter is a mysterious and elusive substance that has yet to be fully understood, but its presence is vital for understanding the behavior of galaxies. Without dark matter, galaxies like Andromeda would not be able to hold themselves together. The gravitational pull of visible matter alone would be insufficient to counteract the outward forces caused by the galaxy's rotation. The discovery of dark matter has fundamentally changed our understanding of the universe, as it suggests that the majority of the mass in galaxies is not made up of the visible stars and gas that we can observe directly. As Andromeda continues to evolve, its dark matter halo will remain a key component of its overall structure. The distribution of dark matter in the galaxy has implications not only for Andromeda itself but also for the broader understanding of galaxy formation and evolution. By studying the way dark matter influences the motion of stars and gas within Andromeda, astronomers can gain valuable insights into the properties of dark matter and its role in shaping the universe. Looking ahead to the future of Andromeda, it's clear that the galaxy's future is intricately tied to the ongoing process of galaxy mergers. As mentioned earlier, the collision between Andromeda and the Milky Way will fundamentally alter both galaxies. This merger will take billions of years to unfold, but once it is complete, it will result in the formation of a single, larger elliptical galaxy. The process of this merger will trigger new bursts of star formation, and the dynamics of the galaxy will be profoundly changed. Ultimately, the fate of Andromeda, like the fate of all galaxies, is tied to the universe's grand cycle of birth, evolution, and death. The collision with the Milky Way will mark a turning point in the history of both galaxies, but it will also be a part of the larger cosmic narrative that plays out across the universe. Galaxies like Andromeda are living entities, constantly evolving and changing as they interact with the universe around them. Their stories are not just the stories of individual galaxies, but of the universe itself, a dynamic, ever-changing system where galaxies, stars, and even black holes come together and collide, creating the ever-expanding cosmos we observe today. As the eventual merger between the Andromeda and Milky Way galaxies looms on the cosmic horizon, we begin to understand that the fates of galaxies are not just dictated by their own internal dynamics but are also shaped by the broader gravitational influences of the universe. The collision of two such massive galaxies as Andromeda and the Milky Way will not simply be a merging of stars. In fact, the majority of the stars in both galaxies will likely pass by one another without any direct collisions. Stars and galaxies are so far apart that even in a merger of this magnitude, the likelihood of direct stellar collisions is extremely low. Instead, the merger will lead to a significant reshaping of the galaxy's structures. The two galaxies will begin to interact gravitationally, distorting their shapes and initiating massive tidal forces that will pull and tug at the stars, gas, and dust within each galaxy. This interaction will likely trigger a burst of new star formation as the gas clouds within the galaxies collide and compress, igniting the formation of new stars. The intense gravitational forces involved in such a merger will also result in the eventual merging of the two supermassive black holes at the centers of the galaxies, creating an even more massive black hole. This process, known as a black hole merger, will release a vast amount of energy in the form of gravitational waves, ripples in spacetime that can be detected by observatories like LIGO. In the aftermath of the merger, the two galaxies will settle into a more stable configuration, likely forming a large elliptical galaxy. This new galaxy will have a very different structure from the spiral shape that Andromeda and the Milky Way currently possess. The spiral arms of both galaxies will be disrupted, and the galaxy's stars will be rearranged into a more diffuse, ellipsoidal shape. The gas and dust that fueled the previous star formation will be depleted during the merger, leading to a decrease in new star formation over time. As a result, this new elliptical galaxy will gradually age, with fewer and fewer new stars being born and the older stars becoming the dominant population. This cosmic dance of galactic mergers is not an isolated event. It is a natural part of the evolution of galaxies throughout the universe. Galaxies, especially larger ones like Andromeda, do not exist in isolation but are part of larger galactic clusters. Over billions of years, galaxies in these clusters will collide and merge, leading to the formation of even larger galaxies. While the immediate effects of such mergers might be violent and dramatic, the long-term outcome is the creation of more stable and mature galaxies. However, it's not just the collision with the Milky Way that will reshape Andromeda's future. The galaxy is also interacting with several smaller galaxies, which are part of its own gravitational influence. These smaller galaxies, including the M32 and M110 galaxies, are satellites of Andromeda. Over time, these smaller galaxies will be drawn into Andromeda's gravitational field, and they too will eventually merge with the larger galaxy. These mergers will add to the growth of Andromeda, helping it to grow larger and more massive as it absorbs smaller galaxies into its fold. One of the key aspects of studying Andromeda's future is understanding how these interactions and mergers affect the central supermassive black hole. As we mentioned earlier, the supermassive black hole in the center of Andromeda, known as M31*, is an essential player in the galaxy's evolution. When the two supermassive black holes of Andromeda and the Milky Way merge, the resulting black hole will likely be one of the largest known. This new, more massive black hole will have a profound impact on the dynamics of the galaxy, influencing the motion of stars and gas in the region surrounding it. In addition to its gravitational influence, the supermassive black hole at the center of Andromeda may also play a role in the galaxy's star formation processes. Supermassive black holes are often thought to regulate the rate of star formation in a galaxy. The intense radiation emitted by the black hole can heat up the surrounding gas, preventing it from collapsing into new stars. This process, known as feedback, can have a significant impact on the overall star formation rate of the galaxy. As Andromeda continues to evolve, the behavior of its supermassive black hole will remain a key factor in determining the galaxy's future. Beyond the merger with the Milky Way and its interactions with smaller galaxies, Andromeda's larger position in the universe also plays a role in its evolution. The galaxy is located within a group of galaxies known as the Local Group, which includes the Milky Way, the Triangulum Galaxy, and several smaller galaxies. The gravitational interactions between these galaxies are already beginning to shape Andromeda's future, and over time, the local group itself will evolve into a more massive galactic cluster. The local group is part of a larger network of galaxies known as the Virgo cluster. Over billions of years, galaxies within the local group will continue to interact with one another, and eventually, the local group will merge with other clusters in the universe. This larger galactic merger will continue the process of galaxy growth, eventually leading to the formation of even larger galaxies. While these interactions are still far off in the future, they highlight the dynamic and interconnected nature of the universe. Galaxies like Andromeda are not isolated entities but are part of a larger cosmic web, where interactions and mergers drive the evolution of the universe on a grand scale. While it may seem as though Andromeda's future is already written, with its eventual collision with the Milky Way and the formation of a new elliptical galaxy, there are still many mysteries that remain about this fascinating galaxy. One of the most significant unanswered questions is the nature of Andromeda's dark matter halo. Dark matter, which makes up most of the mass in the galaxy, has yet to be fully understood. Despite its gravitational influence on the galaxy's stars and gas, dark matter does not interact with light in any measurable way, making it invisible to traditional telescopes. Its presence is inferred through its effects on visible matter, but much about its properties remains a mystery. As scientists continue to study Andromeda and other galaxies, they will undoubtedly make new discoveries that will deepen our understanding of the universe. For now, the Andromeda Galaxy remains one of the most intriguing and accessible objects in the night sky, a symbol of the immense scale and complexity of the universe. Its story, from its formation billions of years ago to its eventual merger with the Milky Way, is a testament to the dynamic nature of the cosmos, where galaxies are born, evolve, and ultimately collide in a never-ending cycle of cosmic activity. Andromeda's history is also a reminder of the vastness of time. The events we've discussed, the formation of stars, the mergers with other galaxies, the evolution of the supermassive black hole, have all taken place over the course of billions of years. And as the universe continues to expand, these events will continue, shaping the future of not just Andromeda but the entire cosmos. The study of galaxies like Andromeda is more than just a glimpse into the past. It's a way of understanding the processes that govern the universe and, ultimately, the fate of everything within it. From the birth of stars to the merging of galaxies, from the mysterious dark matter halo to the powerful forces surrounding its supermassive black hole, Andromeda remains a treasure trove of astronomical wonder. It serves as both a reminder of how much we've learned about the universe and how much we still have left to uncover. As we continue to observe and explore this incredible galaxy, we are not just looking at the past, but also peering into the future of our own galaxy, the Milky Way, and our place in the vast expanse of the universe. And as we look to the distant future, Andromeda will always hold a special place in our understanding of the cosmos. Its evolution, its fate, and its ongoing mysteries will continue to captivate scientists and stargazers alike for generations to come. As we continue to peer deeper into the Andromeda Galaxy, it's essential to consider the galaxy's broader role in the cosmic landscape. While its merger with the Milky Way is a defining future event, Andromeda's interactions with other galaxies and its place within the universe have implications that stretch far beyond the realm of local galactic neighborhoods. Andromeda is part of the local group, a small collection of galaxies that includes the Milky Way, the Triangulum Galaxy, and a handful of smaller satellite galaxies. These galaxies are bound together by gravity, but they are not isolated. They are interconnected in a vast cosmic web of structures that stretches across the observable universe. The local group itself is part of a much larger cosmic structure known as the Laniakea supercluster. This supercluster is a massive collection of galaxies, which includes the Virgo cluster, the gravitational center of the supercluster. Within this immense structure, galaxies like Andromeda and the Milky Way are merely tiny components of a much larger cosmic network. As galaxies within the local group, including Andromeda, continue their orbital dance within the larger framework of the supercluster, they will eventually influence and interact with galaxies far beyond our immediate cosmic neighborhood. Even further beyond the Laniakea supercluster lies the vast and largely unexplored reaches of the universe, where galaxies continue to form and interact in ways we can only begin to comprehend. The study of galaxies like Andromeda provides astronomers with crucial insights into the evolution of galaxies across cosmic time scales. By observing the way Andromeda has evolved, scientists can make inferences about the processes that drive the formation and transformation of galaxies throughout the entire universe. These processes can include the interplay of dark matter, the effects of supermassive black holes, and the gravitational interactions that shape the dynamics of galaxy clusters. The observations of galaxies like Andromeda offer more than just a glimpse into the past. They serve as a window into the future of the universe itself. Andromeda's future merger with the Milky Way will be a profound moment in cosmic history, and the resulting galaxy will likely play an essential role in the next phase of galactic evolution. While galaxies like the Milky Way and Andromeda are the dominant forces within their respective neighborhoods, they are also influenced by the larger structures around them, such as the cosmic voids, dark matter filaments, and galaxy clusters that make up the fabric of the universe. In addition to its stellar content, Andromeda is home to a vast network of interstellar gas and dust that has played a significant role in the galaxy's star formation history. While the majority of stars in Andromeda are thought to be relatively old, there are still areas of active star formation within the galaxy. These regions are found primarily in the spiral arms, where clouds of gas and dust collide, creating the perfect conditions for new stars to form. These star-forming regions are crucial to understanding how galaxies evolve over time, as they provide insight into the processes that fuel the birth of stars and the ongoing development of a galaxy's stellar population. Andromeda's spiral structure, though currently evident, is not a permanent feature. As the galaxy continues its interaction with the Milky Way, it will eventually lose its spiral shape. The merger will lead to a new galactic morphology, likely an elliptical galaxy, where the star formation rate will gradually slow down as the gas and dust resources are consumed or expelled. This transformation is not unique to Andromeda. In fact, many galaxies that undergo major mergers experience similar shifts in structure, and over time, the formation of elliptical galaxies becomes the common endpoint for many once spiral galaxies. But the changes to Andromeda won't be confined to its shape and structure. The galaxy's supermassive black hole, located at the core of the galaxy, will undergo a significant transformation as well. As the Milky Way's black hole merges with Andromeda's, the combined gravitational forces will produce one of the most massive black holes ever seen. This new supermassive black hole will likely have a profound impact on the surrounding stellar population, potentially influencing the dynamics of stars and gas far beyond its immediate vicinity. The future of Andromeda's supermassive black hole is one of the most fascinating and mysterious aspects of the galaxy's evolution. Supermassive black holes are thought to play a key role in regulating the growth and evolution of galaxies, and their influence extends far beyond the central regions of their host galaxies. The black hole at the heart of Andromeda, like its counterpart in the Milky Way, controls the motion of stars and gas in the surrounding regions, shaping the overall dynamics of the galaxy. However, as the merger between Andromeda and the Milky Way progresses, the central black hole will likely experience significant changes. The collision of the two supermassive black holes will release an enormous amount of energy in the form of gravitational waves, and this event will forever alter the central region of the resulting galaxy. The merger of the supermassive black holes will be a moment of cosmic significance. It represents not only the culmination of the galactic collision, but also the dramatic consequences of the immense forces at play in the universe. The newly formed black hole will exert its influence on the surrounding stars, gas, and dust, potentially creating new phenomena such as active galactic nuclei, AGN. AGN are regions around supermassive black holes where the accretion of gas leads to the emission of intense radiation, often outshining the rest of the galaxy. This process can have a profound effect on the galaxy's overall structure, and it can also provide valuable insight into the relationship between galaxies and their central black holes. While the merger of Andromeda and the Milky Way may seem distant in the future, the ongoing observations of both galaxies continue to provide valuable insights into the nature of galaxies and their evolution. The study of galaxies like Andromeda allows scientists to test models of galaxy formation, star formation, and the behavior of supermassive black holes. It also helps astronomers understand the larger cosmic processes that govern the universe, from the formation of galaxy clusters to the dynamics of the vast cosmic web that stretches across space. One of the most intriguing aspects of Andromeda is the mystery of its dark matter halo. Like most galaxies, Andromeda is surrounded by a massive, invisible halo of dark matter, which accounts for a significant portion of its mass. Despite its crucial role in shaping the galaxy's structure and dynamics, dark matter remains one of the most elusive components of the universe. It does not emit, absorb, or reflect light, making it invisible to traditional telescopes. However, its gravitational influence is detectable, and astronomers are working tirelessly to understand its properties. Dark matter is thought to be a key driver of galaxy formation, and it is essential to the stability of galaxies like Andromeda. The dark matter halo helps to keep the galaxy together by providing the gravitational forces necessary to counteract the outward push of the galaxy's stars and gas. Without this unseen mass, galaxies would not have the gravitational pull needed to retain their stars, and they would eventually dissipate over time. While much of the dark matter in Andromeda is still a mystery, scientists have made significant strides in studying its effects on the galaxy. By measuring the motion of stars and gas within the galaxy, astronomers can infer the distribution and density of dark matter in different regions of the galaxy. These observations provide crucial insights into the nature of dark matter and its role in the evolution of galaxies. Understanding the dark matter halo of Andromeda is not just important for studying this particular galaxy. It is also essential for understanding the dark matter that pervades the entire universe. The study of Andromeda's dark matter can help scientists better understand the properties of dark matter itself, shedding light on one of the most profound mysteries of modern physics. As our understanding of Andromeda deepens, we continue to explore the galaxy's stellar content, its dark matter halo, and the role it plays in the larger cosmic structure. But the journey doesn't end here. There are still many more questions to answer, and with each discovery, we come closer to understanding the fate of Andromeda and its ultimate place in the universe. The mysteries surrounding Andromeda don't end with its stellar population, black holes, or dark matter halo. One of the most profound aspects of studying this galaxy is understanding the forces that have shaped its evolution over billions of years. Andromeda's history is a tale of cosmic collisions, star formation, and the slow, inevitable changes that all galaxies undergo. By examining the galaxy's structure and its interactions with neighboring galaxies, scientists can learn about the processes that drive galactic evolution across the universe. As we continue to explore Andromeda's evolution, one of the most significant factors in its formation and development is the role of gravitational interactions. Galaxies are not isolated entities. They are constantly influencing and being influenced by their neighbors. Andromeda, like the Milky Way, has been shaped by its interactions with other galaxies throughout its life. These interactions can lead to everything from minor gravitational perturbations to massive galactic collisions, which can radically change the shape and composition of a galaxy. Andromeda itself has a rich history of gravitational interactions with other galaxies. In fact, the galaxy is currently in the process of merging with a smaller satellite galaxy known as M32. This ongoing merger is one of the primary reasons for the formation of Andromeda's peculiar bulge and its overall irregular appearance. Over the course of billions of years, Andromeda has absorbed smaller galaxies, and the process of accretion has altered the galaxy's structure. These smaller galaxies, now part of Andromeda, have contributed to its overall stellar population and have had a significant impact on its gravitational dynamics. One of the most fascinating aspects of these gravitational interactions is the phenomenon of tidal forces. When two galaxies pass near each other, the gravitational pull of one galaxy can stretch and distort the other. In the case of Andromeda and its satellite galaxies, these tidal forces have caused significant disturbances in the structure of the galaxy. The effects of tidal forces can be seen in the long, faint tidal streams of stars that extend outward from Andromeda, remnants of past interactions with smaller galaxies. These tidal streams serve as a kind of cosmic record, preserving the history of the galaxy's interactions with its neighbors. While Andromeda is currently undergoing mergers with smaller galaxies like M32, Its most dramatic future interaction will be the collision with the Milky Way. This event, which will take place in about 4.5 billion years, will lead to a complete restructuring of both galaxies. During this cosmic collision, the gravitational forces of the two galaxies will cause massive disruptions in their stellar populations. Stars will be flung into new orbits, and some will be ejected from the galaxy altogether. However, despite the chaos that will unfold during the merger, the vast distances between stars mean that direct collisions between individual stars are highly unlikely. Instead, the galactic gas and dust will collide, triggering intense star formation. The outcome of this merger will be the formation of a new, larger galaxy. The Milky Way and Andromeda will eventually coalesce into a single elliptical galaxy, with a large, central bulge of stars and a relatively low rate of ongoing star formation. The resulting galaxy, often referred to as Milkomeda or Milkomeda, will be a much larger and more massive system than either the Milky Way or Andromeda individually. Over time, this galaxy will continue to evolve, with the central supermassive black hole at the heart of the merger becoming even more massive and influential. The future merger of the Milky Way and Andromeda is one of the most exciting prospects in the study of galaxies. While the merger itself is still billions of years away, scientists are already studying the dynamics of galaxies in collision to better understand how these massive cosmic events unfold. By studying galaxies that have already undergone mergers, astronomers are able to develop models of how the Milky Way and Andromeda will eventually merge. These models predict that, after the merger, the two galaxies will settle into a relatively stable configuration, with star formations slowing down as the galaxy's gas supply is used up or expelled. But the merger of the Milky Way and Andromeda is not the only dramatic event that is shaping the galaxy. Andromeda is also home to a number of smaller galaxies that are currently being absorbed or will be in the future. One of these galaxies is the Triangulum Galaxy, which is also part of the local group. The Triangulum Galaxy is a smaller, spiral galaxy that is currently on a collision course with Andromeda. While the Triangulum Galaxy is not as massive as Andromeda, it still has a significant gravitational influence, and its eventual merger with Andromeda will contribute to the overall evolution of the galaxy. In addition to the ongoing mergers with smaller galaxies, Andromeda also plays host to several satellite galaxies of its own. These smaller galaxies orbit around Andromeda, and their stars are bound by the gravity of the larger galaxy. The interactions between Andromeda and these satellites can lead to the formation of tidal streams, which are faint trails of stars that have been pulled away from their parent galaxies. These tidal streams can be used to trace the history of Andromeda's interactions with its satellites, and they provide valuable clues about the galaxy's past. Another fascinating aspect of Andromeda's evolution is the process of star formation. While the majority of stars in Andromeda are relatively old, there are still regions within the galaxy where new stars are being born. These regions are typically found in the spiral arms of the galaxy, where large clouds of gas and dust are compressed by gravitational forces, leading to the formation of new stars. These star-forming regions are often associated with nebulae, which are vast clouds of gas and dust that glow brightly due to the radiation emitted by newborn stars. The study of star formation in Andromeda provides valuable insights into the processes that drive the birth of stars and galaxies. By comparing the star-forming regions in Andromeda with those in other galaxies, astronomers can learn about the conditions that are necessary for star formation and how these conditions vary across different environments. Understanding the process of star formation is essential for understanding the evolution of galaxies, as the rate of star formation determines the overall stellar population of a galaxy and influences its long-term evolution. As we continue to explore the Andromeda Galaxy, it becomes clear that this massive spiral galaxy is not just a neighbor to the Milky Way, it is a key player in the broader story of cosmic evolution. Its stars, gas, dust, and dark matter all interact in complex ways, shaping the galaxy's structure and determining its future. From its interactions with smaller galaxies to its eventual merger with the Milky Way, Andromeda's journey is far from over. As astronomers continue to study this galaxy, we gain a deeper understanding of the forces that shape the universe, and we move closer to answering some of the most profound questions about the nature of galaxies, star formation, and the evolution of the cosmos. As we delve deeper into the intricacies of the Andromeda Galaxy, one of the key questions that arise concerns the galaxy's role in the broader cosmic web. Galaxies like Andromeda don't exist in isolation. They are part of a larger structure known as the local group, a collection of over 54 galaxies that are bound together by gravity. The local group includes not only the Milky Way and Andromeda, but also a number of smaller galaxies, such as the Triangulum Galaxy, the Large and Small Magellanic Clouds, and numerous dwarf galaxies. The interactions between these galaxies are complex and multifaceted, and they offer insights into how galaxies form, evolve, and interact over cosmic time scales. The local group itself is part of an even larger structure called the local supercluster, a vast collection of galaxies that are gravitationally bound to one another. The Milky Way and Andromeda, as the two largest galaxies in the local group, play a significant role in the dynamics of this larger structure. They are often referred to as the dominant galaxies in the local group due to their size and mass. However, the local group is not a static structure. It is constantly evolving as galaxies move and interact with one another. One of the most intriguing aspects of the local group is the gravitational tug-of-war between its two largest members, the Milky Way and Andromeda. These two galaxies are not only the largest but also the most massive members of the group. They are in a slow, inevitable collision course with one another, and this impending merger will have profound implications for the future of the local group. The collision of the Milky Way and Andromeda will significantly affect the smaller galaxies within the group, as their trajectories and interactions with the two giants will be altered by the gravitational forces at play. Some of these smaller galaxies will be absorbed by the larger galaxies, while others may be flung out of the group entirely. In addition to the gravitational interactions between galaxies, another key factor in the evolution of galaxies like Andromeda is the role of dark matter. While dark matter remains one of the most elusive components of the universe, it is thought to play a crucial role in the formation and evolution of galaxies. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it invisible to our current telescopes. However, its presence can be inferred through its gravitational effects on visible matter. It is believed that dark matter makes up about 85% of the mass of the universe, and its influence can be seen in the way galaxies like Andromeda rotate. In the case of Andromeda, dark matter is thought to form a vast, diffuse halo around the galaxy, extending far beyond the visible stars and gas that we can observe. This dark matter halo exerts a gravitational pull on the visible matter in the galaxy, helping to keep the stars, gas, and dust bound together. Without the presence of dark matter, Andromeda would likely have flown apart long ago. The existence of dark matter in Andromeda can be inferred from the galaxy's rotation curve, which shows that the stars at the outer edges of the galaxy move at much higher speeds than would be expected based solely on the visible matter. This observation is one of the key pieces of evidence for the existence of dark matter in the universe. While dark matter is an essential component of Andromeda's mass and structure, it is not the only mysterious substance that is believed to be present in the galaxy. Andromeda, like many other galaxies, is thought to be surrounded by a vast halo of hot, ionized gas. This gas, which is difficult to observe directly, is believed to be a significant component of the galaxy's overall mass. It is thought to play a crucial role in the galaxy's evolution, as it provides a reservoir of material from which new stars can form. This hot gas is also thought to be responsible for some of the galaxy's most energetic phenomena, such as supernovae and the formation of black holes. Supernovae, the explosive deaths of massive stars, are one of the most dramatic events that occur within galaxies like Andromeda. These explosions release enormous amounts of energy, enriching the surrounding gas with heavy elements and triggering the formation of new stars. Supernovae are a key part of the life cycle of stars and play an important role in the chemical evolution of galaxies. The heavy elements produced by supernovae are distributed throughout the galaxy, enriching the interstellar medium and making it possible for future generations of stars to form with a higher concentration of elements like carbon, oxygen, and iron. In addition to their role in star formation, supernovae are also important for the formation of black holes. When a massive star runs out of fuel and collapses under its own gravity, it can form a black hole at its core. The formation of black holes is one of the most mysterious and fascinating aspects of astrophysics, and Andromeda is home to several supermassive black holes, including one at its center. The presence of these black holes has a profound effect on the galaxy, influencing its structure, star formation, and even the motion of stars and gas within the galaxy. One of the most intriguing questions about Andromeda, and galaxies in general, is the role of the supermassive black hole at the center of the galaxy. This black hole, known as the Andromeda black hole, is thought to be millions of times more massive than the Sun. Like other supermassive black holes, it exerts a powerful gravitational pull on the stars and gas in its vicinity. The black hole's gravity is so intense that it can warp the spacetime around it, creating a region where nothing, not even light, can escape. The study of these black holes is one of the most exciting areas of astrophysical research, as they offer a unique opportunity to study the fundamental laws of physics under extreme conditions. In Andromeda, the supermassive black hole at the center of the galaxy is thought to play a crucial role in regulating the galaxy's growth and evolution. It is believed that the black hole's gravity influences the formation of stars in the central regions of the galaxy, as well as the overall dynamics of the galaxy. In some cases, supermassive black holes can even trigger the formation of new stars by heating up the surrounding gas and causing it to collapse. This process, known as active galactic nucleus (AGN) feedback, is thought to be a key driver of galaxy evolution. The study of Andromeda's central black hole is ongoing, and scientists are using a variety of tools to learn more about this mysterious object. Observations of the galaxy's central region, using telescopes like the Hubble Space Telescope and the Chandra X-ray Observatory, are providing valuable insights into the behavior of the black hole and its influence on the surrounding stars and gas. These observations are also helping to refine our understanding of the role of supermassive black holes in the evolution of galaxies and the broader universe. The study of Andromeda is a journey of discovery, one that has provided scientists with a wealth of information about the nature of galaxies, star formation, black holes, and the fundamental forces that govern the universe. As technology advances and new observational tools are developed, our understanding of this distant neighbor will continue to grow, offering new insights into the cosmos and our place within it. The Andromeda Galaxy, with its complex history and dynamic future, is not just a point of light in the night sky. It is a living, evolving system that holds the secrets to the formation and evolution of galaxies across the universe. The exploration of the Andromeda Galaxy continues to yield new discoveries, and as our technology advances, the mysteries of this distant celestial neighbor are becoming more accessible to scientists and astronomers alike. One of the key tools in understanding the Andromeda Galaxy is the study of its structure, which, much like our own Milky Way, reveals a complex and evolving system of stars, gas, dust, and dark matter. At the heart of Andromeda, the supermassive black hole plays a pivotal role, not only in the dynamics of the galaxy but also in shaping its interactions with other galaxies. This black hole is situated at the center of a dense cluster of stars, and its gravitational influence extends far beyond the immediate vicinity of the galactic core. It is believed that supermassive black holes, such as the one in Andromeda, are critical in the formation and evolution of galaxies. They help regulate star formation, the distribution of gas, and the overall evolution of the galaxy over billions of years. As we observe the core of Andromeda, one of the most striking features is the presence of a prominent bulge at the center, formed by a dense concentration of stars. This bulge is a common feature in spiral galaxies, and it plays a central role in the galaxy's overall structure. The bulge is surrounded by a disk of stars, gas, and dust, which extends outward in a spiral pattern. These spiral arms, which give the galaxy its characteristic shape, are home to many of Andromeda's most active regions of star formation. These arms are composed of dense clouds of gas and dust, which collapse under gravity to form new stars. These regions are often illuminated by the bright, young stars that are born within them, making the spiral arms some of the most vibrant and energetic parts of the galaxy. Beyond the spiral arms lies the galactic halo, a vast region of space that extends far beyond the visible stars of the galaxy. This halo is composed of stars, gas, and dark matter, and it is thought to be a remnant of the galaxy's early history. The stars in the halo are generally older and less concentrated than those in the disk, and they can provide valuable insights into the formation and evolution of the galaxy. The dark matter in the halo plays a crucial role in the galaxy's overall mass distribution, helping to hold the galaxy together and influencing its rotation curve. As we peer further into the Andromeda Galaxy, it becomes clear that it is a dynamic and ever-changing system. The interactions between its stars, gas, and dark matter have shaped the galaxy over billions of years, and will continue to do so for billions more. One of the most dramatic changes on the horizon for Andromeda is its eventual collision with the Milky Way. While this event may seem far off, estimated to occur in about 4.5 billion years, it is a certainty that will have profound effects on both galaxies. The collision will not be a catastrophic event in the way we might imagine a collision between solid objects. Rather, it will be a slow, gravitationally driven merger that will reshape both galaxies over time. During this collision, the stars within both galaxies are unlikely to collide directly with one another, given the vast distances between individual stars. However, the gravitational forces at play will cause the galaxies to interact in dramatic ways. The collision will trigger new waves of star formation as gas clouds are compressed, and it will likely result in the formation of a new, elliptical galaxy. The supermassive black holes at the centers of both the Milky Way and Andromeda will likely merge, creating an even larger black hole that will dominate the newly formed galaxy. In the aftermath of the merger, the combined galaxy will be a vastly different place than either the Milky Way or Andromeda is today. The once defined spiral arms will likely be smoothed out, and the galaxy's interstellar gas will be dispersed. This transformation will mark the end of one chapter in the life of these galaxies, and the beginning of a new era. While the Milky Way and Andromeda may no longer resemble their current forms, the collision will ensure that both galaxies continue to evolve, albeit in a very different way. While this cosmic collision is still billions of years away, it serves as a reminder of the ever-changing nature of the universe. Galaxies are not static entities. They are dynamic, evolving systems that are constantly interacting with one another, shaped by the forces of gravity, dark matter, and the birth and death of stars. Andromeda, like the Milky Way, is a part of a much larger cosmic tapestry, and its future is inextricably linked to the future of its cosmic neighbors. In addition to the physical interactions between galaxies, the study of Andromeda also provides valuable insights into the broader structure of the universe. Galaxies are not evenly distributed across space. Rather, they are organized into vast cosmic structures known as galaxy clusters and superclusters. Andromeda, as a member of the local group, is part of the local supercluster, a vast region of space that contains many galaxies, including our own Milky Way. The study of galaxy clusters and superclusters helps astronomers understand how galaxies are distributed across the universe, and how they interact with one another on the largest scales. One of the most intriguing aspects of the study of Andromeda is the role of dark matter. This mysterious substance, which makes up about 85% of the mass of the universe, cannot be seen directly, but its presence can be inferred through its gravitational effects. Dark matter is thought to play a crucial role in the formation and evolution of galaxies, including Andromeda. The presence of dark matter is believed to help hold galaxies together, preventing them from flying apart due to the rotational forces exerted by the stars and gas within them. In Andromeda, the dark matter halo is believed to extend far beyond the visible stars, helping to maintain the galaxy's structure and influence its rotation. While dark matter remains one of the greatest mysteries in astrophysics, its effects on galaxies like Andromeda are clear. By studying the motion of stars and gas within the galaxy, astronomers can infer the distribution of dark matter in Andromeda's halo. These studies have shown that the galaxy's dark matter is spread out in a diffuse, extended halo that is much larger than the visible galaxy itself. This discovery has profound implications for our understanding of galaxy formation, as it suggests that dark matter played a critical role in the early stages of Andromeda's formation. In addition to dark matter, another important component of Andromeda is the hot, ionized gas that surrounds the galaxy. This gas, which is difficult to observe directly, is believed to be a key factor in the galaxy's evolution. It is thought to provide the material from which new stars can form, and it plays a role in the galaxy's overall energy balance. The hot gas is also believed to be responsible for some of the galaxy's most energetic phenomena, such as the formation of supernovae and black holes. Supernovae, the explosive deaths of massive stars, are some of the most dramatic events in the life of a galaxy. These explosions release enormous amounts of energy and scatter heavy elements into the surrounding gas, enriching the interstellar medium and contributing to the formation of new stars. In Andromeda, supernovae are relatively common, and they play a crucial role in the galaxy's chemical evolution. The elements produced by these explosions are incorporated into future generations of stars, making them richer in heavy elements than earlier generations. As we continue to study Andromeda and its many mysteries, it becomes clear that this galaxy is a living, evolving system. From its supermassive black hole to its complex network of stars, gas, and dark matter, Andromeda offers a glimpse into the dynamic processes that shape galaxies across the universe. The study of Andromeda is not just about understanding this single galaxy, but also about gaining insights into the broader forces that govern the cosmos. The future of Andromeda, as well as its relationship with the Milky Way, is an exciting area of research that will continue to captivate scientists and the public alike. While the merger between the two galaxies may seem distant, it is a reminder of the constantly evolving nature of the universe and the profound changes that await us in the far future. As we learn more about Andromeda, we are not just uncovering the secrets of this distant galaxy. We are also learning more about the fundamental processes that govern the cosmos and our place within it. As we continue to explore Andromeda's role in the greater universe, it's important to remember that the galaxy isn't just a collection of stars and cosmic dust. The interactions within it are key to understanding both its present and its future. A large part of this comes from the way Andromeda interacts with its neighboring galaxies, most notably the Milky Way. These galaxies are part of the Local Group, a collection of over 54 galaxies bound together by gravity. While Andromeda and the Milky Way are the two largest galaxies in this group, there are also smaller galaxies that influence the overall dynamics of this region of space. One of the more fascinating aspects of the Local Group is the gravitational tug-of-war between Andromeda and the Milky Way. As they pull on each other, they have shaped not only their own individual histories, but also the surrounding galaxies. The gravitational forces between the galaxies have been responsible for a number of phenomena, including the formation of satellite galaxies. These are smaller galaxies that orbit around larger ones, often affected by the tidal forces of the larger galaxy. Andromeda, for example, has several smaller satellite galaxies, and the Milky Way does as well, such as the Magellanic Clouds. These interactions can cause galaxies to lose stars and gas, which may then get incorporated into the larger galaxy or expelled entirely. The impact of these interactions becomes even more significant when we consider the future collision of the Milky Way and Andromeda. While it may be billions of years away, the gravitational forces at play during this merger will significantly alter both galaxies and may lead to the formation of a whole new galaxy. The cosmic dance of these two giants will continue for billions of years before finally merging, with all the effects that a galactic collision entails. While it is true that the stars in these galaxies are unlikely to collide directly, their gravitational influence will be felt in every corner of both galaxies. This will likely trigger massive bursts of star formation, as gas clouds compress and collapse under the strain. But the long-term effect will be the eventual reshaping of both galaxies, likely transforming the familiar spiral structure of Andromeda and the Milky Way into something new, an elliptical galaxy. In fact, Andromeda's own interactions with its satellites have had significant consequences. Over time, some of these smaller galaxies have been pulled into Andromeda, where they have either been consumed or transformed through tidal interactions. This process of galactic cannibalism is common in the universe and happens across various scales. Smaller galaxies may be absorbed by larger ones as they slowly spiral toward their larger neighbors, contributing to the growth of the galaxy and altering its structure. This process has undoubtedly played a part in the formation of Andromeda, making it the massive galaxy we see today. One of the most remarkable things about Andromeda is how it provides us with insights into the past and future of the Milky Way. As we continue to study the structure, composition, and behavior of Andromeda, we're not just learning about one galaxy in isolation, but about the fundamental processes that govern all galaxies, including our own. As astronomers continue to investigate Andromeda's supermassive black hole, its dark matter halo, and the remnants of its ancient satellites, they are building a clearer picture of how galaxies grow, evolve, and eventually collide. A major part of this ongoing study involves looking at Andromeda's stellar population. The galaxy is home to billions of stars, each with its own history and place in the galaxy's evolutionary timeline. Some stars in Andromeda are relatively young, born from the galaxy's rich supply of gas and dust, while others are ancient, relics of the galaxy's early formation. By studying these stars and their composition, astronomers can learn about the different stages of galaxy formation and the processes that have led to Andromeda's current state. Additionally, the stars in Andromeda serve as valuable analogues for studying the stars in the Milky Way, offering a more accessible laboratory for understanding the properties of distant stars. But Andromeda's stellar population is not just about the stars we see. There is also a significant amount of invisible matter, dark matter, that plays an essential role in shaping the galaxy. Dark matter is believed to make up the majority of the mass of galaxies like Andromeda, yet it cannot be directly observed. Its presence is inferred by the gravitational effects it has on visible matter, such as stars and gas. In Andromeda, dark matter is thought to form a vast, spherical halo that extends well beyond the visible galaxy. This dark matter halo helps to stabilize the galaxy and affects its overall motion and evolution. The interaction between dark matter and visible matter within Andromeda provides clues not just to the galaxy's structure, but to the nature of dark matter itself. Despite being one of the most abundant components of the universe, dark matter remains one of the greatest mysteries in modern astrophysics. Studying galaxies like Andromeda, where dark matter plays such a crucial role, is one of the ways astronomers are attempting to unlock the secrets of this elusive substance. As we look even deeper into the Andromeda Galaxy, one of the most profound revelations is how the galaxy fits into the grander scale of the universe. Andromeda is not just an isolated entity, it's part of a much larger cosmic web that stretches across vast distances, connecting galaxies in intricate and often surprising ways. The universe is not randomly distributed, rather, galaxies tend to cluster together, bound by gravity into galaxy groups and superclusters. Andromeda, as part of the local group, is a member of a much larger supercluster of galaxies, which also includes the Milky Way. By studying how Andromeda and its neighbors are arranged in the universe, we can begin to understand the large-scale structure of the cosmos. This larger cosmic structure is thought to be shaped by the distribution of dark matter. While we cannot directly observe dark matter, its presence can be inferred through its gravitational effects. It is believed that dark matter acts as a scaffolding for the formation of galaxies, galaxy clusters, and superclusters. By studying the distribution of galaxies in clusters like the local group, astronomers can gain insights into the role that dark matter plays in shaping the overall structure of the universe. In addition to providing insights into the large-scale structure of the universe, the study of Andromeda also helps us understand the broader processes of galaxy evolution. Galaxies like Andromeda are not static objects, they are constantly changing, evolving under the influence of a variety of forces. The ongoing interaction between Andromeda and the Milky Way, as well as the gravitational interactions within the local group, are shaping both galaxies, altering their structure, and influencing their future evolution. As we continue to observe and study these galaxies, we are not only learning about Andromeda but also about the broader forces that govern the universe as a whole. One of the most exciting aspects of this study is the role that technological advancements will play in our understanding of galaxies like Andromeda. New telescopes and instruments are constantly being developed, allowing astronomers to peer deeper into space and gather more detailed information about distant galaxies. For example, the upcoming James Webb Space Telescope promises to provide unprecedented views of the universe, including detailed observations of galaxies like Andromeda. With these new tools, we are on the verge of making discoveries that could completely reshape our understanding of galaxies, dark matter, and the universe itself. As we continue to observe Andromeda, we are not just learning about this single galaxy but about the very nature of the universe. Each new discovery, whether it's about the galaxy's structure, its dark matter halo, or its interaction with the Milky Way, brings us closer to understanding the fundamental processes that govern galaxies and the larger cosmos. The future of Andromeda, both as a subject of scientific study and as a potential merger partner for the Milky Way, promises to be just as exciting and mysterious as its past. As we continue to delve deeper into Andromeda, we must consider not just its immediate cosmic neighborhood but also its position within the broader universe. While the Milky Way and Andromeda are often depicted as the primary players in the local group, there are other galaxies that contribute to the overall dynamic. These include galaxies like the Triangulum Galaxy, another major member of the local group, as well as many smaller dwarf galaxies scattered around. However, it's Andromeda and the Milky Way that dominate this group, and their relationship is key to understanding not only their future but also the future of galaxies in general. One of the most fascinating aspects of Andromeda is how it has evolved over time. When we look at its spiral structure, its active core, and the various star systems within it, we see evidence of the galaxy's history written in its stars and gas clouds. The galaxy has undergone several episodes of growth and transformation. Its present form is the result of billions of years of stellar evolution, galaxy mergers, and cosmic interactions. One of the major factors influencing Andromeda's growth has been the process of galactic accretion. This refers to the way in which galaxies grow by gradually accumulating gas, dust, and smaller galaxies over time. This is a natural part of galaxy evolution, and Andromeda has experienced this process on a grand scale. As the galaxy pulled in smaller satellite galaxies and gas clouds, it grew in mass and complexity. The influence of its supermassive black hole at the center of the galaxy has also played a role, shaping the behavior of stars and gas within the galaxy and contributing to the overall dynamics of the galaxy's spiral arms. At the heart of Andromeda lies its supermassive black hole, a behemoth that is many millions of times more massive than our Sun. Like other supermassive black holes, it exerts a profound influence on the surrounding stars, gas, and dust. The black hole's gravity pulls material inward, creating a swirling accretion disk that heats up to extreme temperatures, emitting powerful radiation that can be detected by astronomers. This radiation can provide valuable insights into the conditions around the black hole, as well as the broader processes at work within the galaxy. The presence of a supermassive black hole at the center of Andromeda suggests that the galaxy may have undergone dramatic growth phases in the past, possibly fueled by the accretion of nearby galaxies or the merger of star clusters. Despite its size and prominence, Andromeda's supermassive black hole is just one piece of the puzzle when it comes to understanding the galaxy's behavior. The larger structure of Andromeda, including its spiral arms and the distribution of stars, is influenced by the gravitational interactions between the galaxy's stars, gas, and dark matter. The balance between these forces plays a crucial role in shaping the galaxy's shape, movement, and overall evolution. In many ways, Andromeda serves as a laboratory for studying galaxy formation and evolution, providing clues about how galaxies grow, merge, and change over time. Another intriguing feature of Andromeda is its interaction with its satellites and the nearby galaxies in the local group. These interactions have been ongoing for billions of years and have left their mark on the galaxy's structure. As we mentioned earlier, Andromeda is a member of the local group, and it has several satellite galaxies that orbit around it. These satellites are not just passive objects, they are actively affected by Andromeda's gravitational forces, which have shaped their shapes and orbits over time. Some of these galaxies are in the process of being absorbed by Andromeda, while others remain in stable orbits, locked in a cosmic dance with the larger galaxy. In addition to the satellite galaxies, Andromeda is also part of a larger cosmic web of galaxies that stretches across vast distances. The local group, while it contains more than 50 galaxies, is just one small region within this larger structure. Galaxies are not distributed randomly across the universe. They are found in clusters, with gravity pulling them together to form larger structures known as superclusters. Andromeda's position within the local group places it within the Virgo supercluster, a massive collection of galaxies that spans hundreds of millions of light-years. Understanding Andromeda's role within the context of the Virgo supercluster and the larger universe provides valuable insights into how galaxies interact, merge, and evolve over time. The study of Andromeda has also provided valuable information about the role of dark matter in galaxy formation and behavior. While dark matter cannot be directly observed, its presence can be inferred from its gravitational effects on visible matter. Andromeda, like all galaxies, is believed to be surrounded by a halo of dark matter that extends well beyond the visible stars and gas. This dark matter halo plays a crucial role in stabilizing the galaxy, preventing it from flying apart due to the motion of its stars. The distribution of dark matter in Andromeda can provide clues about the overall distribution of dark matter in the universe and help scientists better understand the mysterious substance that makes up a large portion of the mass in the cosmos. The ongoing observations of Andromeda's movement, structure, and interaction with other galaxies are helping to refine our understanding of galaxy evolution. As we observe how Andromeda behaves over time, we gain valuable insights into the forces that shape galaxies and the processes that drive their growth and transformation. The upcoming advent of new telescopes, such as the James Webb Space Telescope, will allow scientists to study Andromeda in even greater detail, opening up new avenues of discovery. These advanced tools will give us a clearer picture of the galaxy's structure, its star formation history, and its future evolution, helping us answer questions that have been on the minds of astronomers for centuries. While Andromeda is one of the most studied galaxies in the universe, it is far from unique. In many ways, it serves as a model for understanding how galaxies form, evolve, and interact with one another. By studying Andromeda, scientists are able to learn about the fundamental processes that govern all galaxies, providing insights that extend far beyond our own cosmic neighborhood. Andromeda is not just a galaxy, it is a key to unlocking the mysteries of the universe itself. Every observation, every new discovery brings us closer to understanding the forces that shape the cosmos, from the smallest stars to the largest galaxy clusters. In conclusion, Andromeda stands as a testament to the complexity and wonder of the universe. From its supermassive black hole to its stellar populations, its satellite galaxies to its dark matter halo, this giant spiral galaxy is a crucial piece of the cosmic puzzle. As we continue to study Andromeda, we are not just learning about a single galaxy. We are learning about the very nature of galaxies, stars, and the universe itself. And as we look to the future, the eventual collision between the Milky Way and Andromeda promises to be one of the most awe-inspiring events in the history of the cosmos. But for now, Andromeda remains a source of endless fascination, a galaxy that continues to reveal its secrets and challenges us to expand our understanding of the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.